In 1981, a team of astronomers directed their instruments toward a seemingly unremarkable dark area of the sky, nestled between constellations, and what they observed was a profound absence. They had uncovered a spherical volume of space, an immense void stretching 330 million light-years from one side to the other. This was a region where calculations suggested some 2,000 galaxies ought to exist, yet only 60 could be found. This colossal emptiness became known as the Boötes Void. For many years, the prevailing view was that it was simply an unusual manifestation of the universe's vast, empty stretches. More recent observations, however, have detected something within its depths, something that appears to be in motion, emitting pulses of energy, and whose very presence seems to defy the known laws of physics for such a desolate environment. The discovery of what lies hidden within this void has the potential to reshape our understanding of the cosmos. The story of its discovery began as routine work for Robert Kirshner and his colleagues in 1981. They were engaged in mapping the positions of galaxies, anticipating a fairly uniform distribution across the cosmos, much like how stars populate our own night sky. Their instruments, however, revealed a chasm, not a minor one, but a vast domain where the presence of galaxies simply ceased. After checking their equipment 3 times, the team found the readings remained stubbornly consistent. As they extended the scope of their survey, tracing the boundaries of this emptiness, it continued to expand until they finally understood they were looking at a structure 330 million light-years wide. To grasp this immense distance, one might imagine our own Milky Way galaxy scaled down to the size of a single quarter. To span the void, you would need to place 33 million of these quarters in a continuous line. Light itself, traveling at 671 million miles per hour, needs 330 million years to complete the journey from one side to the other. The team named it the Boötes Void, after the constellation where it was found. Their calculations, based on the average density of matter in the universe, indicated that this volume of space should contain a minimum of 2,000 galaxies. When they counted what was actually there, the number was a mere 60. This meant that 97% of the expected galactic population had either vanished or had never formed in the first place. This finding sent shockwaves through the field of astronomy, because voids of this magnitude were not predicted by our models of cosmic evolution. The standard view holds that matter should be distributed more evenly throughout space. It appeared something had actively carved out this region, leaving almost nothing behind. And yet, a more unsettling detail emerged from the data. The 60 galaxies that do reside there are not scattered randomly. They are arranged in thin, chain-like structures along the void's periphery, as if they are actively fleeing something at the center, as if they know not to venture too deep inside. When Kirshner published his team's findings, astronomers around the world quickly directed their own instruments toward this area of the sky. Every observation confirmed the same reality, a sphere of almost perfect emptiness suspended in space. The initial consensus among most scientists was that it must be an unusual statistical quirk, a cosmic accident. The universe, after all, can produce strange outcomes. But the void continued to reveal more unusual characteristics. The few galaxies within it displayed strange properties. The spectra of their light seemed incorrect, and their velocities did not align with predictions. There was a sense that the space itself was somehow different. Then, 4 decades later, energy signatures were detected emanating from deep within that emptiness. These signals formed repeating patterns and hinted at structures that should not be able to form in a void. The central question evolved from asking why the region was so empty to what, precisely, was hiding inside it. Empty space, by definition, does not emit organized signals or arrange itself into complex patterns. Whatever was discovered in there is an active phenomenon, and we must understand what is happening. Our standard model of the universe works much like a recipe. It begins with the Big Bang, to which we add dark matter and dark energy. We then sprinkle in ordinary matter and allow gravity to shape the mixture over 13.8 billion years. The expected outcome is the cosmic web, a vast network of galactic filaments resembling spider silk, interspersed with smaller voids. In this model, the largest voids should measure about 150 million light-years across, perhaps reaching 200 million in the most extreme scenarios. This is what the mathematics predicts, and it is what we observe in most of the universe. The Boötes Void, at 330 million light-years across, nearly doubles the maximum size our physics can account for. This is not a minor discrepancy. The inconsistency is significant, akin to a biological model predicting human height tops out at 6 feet, only to discover an individual who is 12 feet tall. Such a difference demands an explanation. The reason this is so important lies in the conditions of the early universe. At that time, matter was distributed with near-perfect uniformity. Tiny quantum fluctuations created regions that were slightly denser or slightly less dense than average. Over billions of years, gravity amplified these differences, pulling matter from the less dense zones into the denser ones. This process is what sculpted the voids and the galactic walls that surround them. However, gravity operates at a finite speed. It can only draw matter across a certain distance within the age of the universe. When we run the calculations in reverse, we find that forming a void of this size would require either far more time than the universe has existed, or forces much stronger than gravity can provide. Neither of these possibilities aligns with our current understanding. The universe is not older than we have measured, and the strength of gravity has not changed. And yet, the void is there, a hole in the fabric of reality that seems to violate the rules. Some physicists have proposed that dark energy might have expanded this region more rapidly than others. As dark energy is the force that pushes space apart, perhaps a concentration of it inflated the void beyond its typical limits. This theory seems plausible at first, but the mathematics does not support it. Even with a maximum concentration of dark energy, a void of this size cannot be created without violating other known cosmic constraints. Another idea is that this region of space simply started out with far less matter than average, a statistical anomaly on an immense scale. The probability of such an event, however, is calculated to be virtually zero. The truth is that we lack any standard explanation that fits the evidence. The Boötes Void should not exist according to our most reliable physics, yet every telescope that observes it confirms its presence. This implies that either our understanding of cosmic evolution is fundamentally flawed, or something entirely different occurred here that we have not yet discovered. Recent observations lean strongly toward this second possibility. Voids are supposed to be passive features of the cosmos. Empty regions do not actively do anything. They simply exist. They certainly do not emit organized patterns of energy, but the Boötes Void is doing just that, which suggests it is not merely a void. It appears to be something far more enigmatic, masquerading as empty space. When you stand outside on a clear night and gaze upward, every star you can see is a member of our own galaxy. Even the most distant, faint point of light is located within about 100,000 light-years of Earth. This is our immediate cosmic neighborhood, the scale of our local reality. To begin to comprehend the sheer scale of the Boötes Void, one might imagine a distance and then increase it by a factor of 3,300. This calculation reveals the void's diameter, an immense expanse that covers 330 million light-years of space. A journey to cross this region, even traveling at the speed of light, would take longer than the entire history of complex life on our planet, repeated several times over. There is another way to visualize this emptiness. Consider our own Milky Way galaxy, home to some 200 billion stars. Now, picture another galaxy of similar size placed 50 million light-years away. Continue this process, adding another and then another, arranging 2,000 of these massive star systems into a great sphere. Finally, remove 97% of them from that sphere. What remains are just 60 galaxies, scattered thinly around the periphery. This is the reality of what we are observing. The void possesses enough volume to accommodate thousands of galaxy superclusters. These are the very regions where millions of galaxies should be gravitationally clustering together. They ought to be forming the largest known structures in the cosmos. Instead, what we perceive is darkness and a profound silence. It is a cosmic dead zone that extends far beyond our ability to truly grasp. Light embarking on a journey from one side of this void requires 330 million years to arrive at the opposite side. When that light first began its transit, the most sophisticated life on Earth was nothing more than single-celled organisms. There were no plants, no animals, and certainly no humans. In the time it takes for that light to complete its crossing, entire species have evolved on our world and vanished into extinction many times. This is not merely large. From a human standpoint, this scale is functionally without limit. One could line up 75,000 Milky Way galaxies, side by side, to span this emptiness. Our entire local group of galaxies could be lost within its confines, never to be found again. The void could easily contain every single galaxy humanity has ever documented through telescopes and still possess an abundance of empty room. And yet, for all its incomprehensible size, astronomers were able to map the entire structure in only a few years. How was this possible? It is because emptiness itself leaves a distinct signature. In a region where galaxies should be emitting light, this area shows only darkness. Where vast amounts of matter should be warping the fabric of space, the void leaves it almost perfectly flat. It is as conspicuous as a missing tooth in an otherwise complete smile. But its dimensions alone do not explain the persistent scientific focus on this region. Space is filled with many large structures. The unsettling quality of the void is not simply its size, it is what that size implies. The void demonstrates that our universe is capable of producing areas where the standard principles appear to cease their function. It is a place where cosmic evolution does not yield the anticipated outcomes. It suggests a place where something fundamental has broken down. If such an impossible emptiness could be formed once, what might prevent it from occurring again? What is to stop other regions of space from acquiring these same characteristics? Could it be that voids like this one are actively spreading? The clue to this puzzle came from a source that was entirely unexpected. It came from the 60 galaxies that seem to refuse to depart. Gravity is not the only force that shapes the universe. It has a counterpart, an influence that pushes outward rather than pulling inward. We refer to this force as dark energy, and it constitutes 68% of everything in existence. The contest between these two forces unfolds in a specific way. In the very early universe, matter was distributed with near-perfect uniformity in every direction. Extremely small variations in density did exist, but they were no greater than 1 part in 100,000. In the slightly denser areas, gravity began to take hold. It drew in the surrounding matter, giving rise to the first stars and galaxies. Over vast timescales, these zones became progressively denser. However, in the slightly emptier regions, the reverse process took place. With less matter available, the pull of gravity was weaker. Dark energy, which exerts a uniform push everywhere, started to become the dominant force. It began shoving the sparse remaining matter outward, making these zones even more evacuated. As they grew emptier, the influence of dark energy became even stronger. This is the process that created the voids. One could think of them as anti-galaxies. They are the places where dark energy won the cosmic contest against gravity. Matter was driven out of these regions, accumulating along their boundaries. This process formed the great walls of galaxies that we see today. The interiors, meanwhile, became increasingly desolate as cosmic time passed. Most voids expand at a slow and steady rate. They begin as small underdensities and grow over billions of years as dark energy continues to push matter away. Their rate of growth is determined by their initial emptiness and the density of the space surrounding them. When we run cosmological simulations, we get a predictable distribution of voids. There are many small ones, a smaller number of medium-sized ones, and almost no truly large ones. The Boötes Void defies this distribution entirely. It exists far beyond the size range that our models can account for. This remains true even when we factor in maximum expansion rates and the most optimal initial conditions. It seems impossible to grow a void to this magnitude within the available age of the universe, unless some other factor was involved. A number of cosmologists have suggested that the void might have been created by a bubble collision in the first moments after the Big Bang. During the period of cosmic inflation, space expanded faster than light for a fleeting instant. If two of these expanding bubbles happened to collide and merge, they could have created an underdense area that later grew into this enormous void. This theory has some merit. A bubble collision could potentially explain the exceptional size. However, it would require a precise timing and positioning that seems highly improbable. It also fails to explain some of the other anomalies that have been detected. Other scientists propose that the void may have originated from primordial quantum fluctuations that were scaled up to a cosmic size. Imagine a region where quantum uncertainty resulted in slightly less matter than the average. Over billions of years, this minuscule deficit could have been amplified, eventually producing this massive emptiness. This is also a possibility. But again, the probability calculations do not support it. Random chance very rarely produces outliers of this extremity. The truth is that we continue to propose new theories because the standard explanation is completely inadequate. Voids are supposed to be simple structures. Matter departs from them. Dark energy takes over. The region remains empty. It should not be complicated. Yet, the Boötes Void refuses to adhere to this simple model. It grew far too large. Its interior exhibits unexpected forms of activity. The galaxies found within it show some very strange properties. Every aspect of this void suggests that something beyond the normal formation process took place here. And when those unusual energy patterns were detected last year, the entire conversation changed. Now, we are no longer just asking how the void was formed. We are asking what might have moved in afterward. Most voids do contain at least a few galaxies. Typically, a few dozen are scattered throughout their interiors. These galaxies either formed early in the universe's history, before the void was fully cleared out, or they drifted in later from the surrounding areas. Their presence is not considered unusual. The 60 galaxies inside the Boötes Void are different. They seem to defy several established principles at once. The first anomaly is their location. They completely avoid the center of the void. Instead, they are clustered along its edges. They are arranged in delicate, thread-like structures. This distribution is gravitationally nonsensical. If these galaxies had formed naturally inside the void, they should be spread out more evenly. If they had fallen in from the outside, they should have been drawn toward the center, where the gravitational potential is at its lowest point. What is immediately striking is their location. Rather than drifting freely, the galaxies seem to adhere to the void's inner surfaces, as if anchored by a force we cannot perceive. A second curiosity is their profound age. An analysis of their light reveals these are ancient stellar systems containing stars that ignited when the cosmos was in its youth. This finding is highly irregular, since galaxies in voids are typically small and young, having formed more recently from leftover gas. The galaxies within Boötes, however, resemble massive, mature elliptical galaxies, the kind that should reside in dense clusters, not in the loneliest expanse of observable space. This raises a fundamental question. How did such old, massive galaxies come to be in this immense emptiness? If they had migrated from elsewhere, their current motion does not align with that possibility. Some other process appears to have placed them in these exact positions. A third puzzle lies in their velocities. The movement of any galaxy is dictated by the gravitational fields in its vicinity. By measuring its motion, astronomers can map the distribution of mass around it. Yet the galaxies in Boötes move in a way that is inconsistent with their surroundings. Their speeds suggest they are being influenced by the gravity of matter that simply is not there, matter that is entirely invisible to us. While one might suspect dark matter is the cause, as it provides the unseen mass affecting galactic motion throughout the universe, voids are specifically defined by their lack of dark matter. The very process that created the void cleared out dark matter along with ordinary matter. Despite this, the galaxies inside Boötes behave as though they are enveloped in a halo of dark matter, as if the void is not truly empty. Fourth, their light presents its own set of enigmas. Every galaxy broadcasts radiation across the electromagnetic spectrum, from visible light to radio waves and X-rays, and this spectrum reveals details about its composition and level of activity. The galaxies in Boötes exhibit peculiar spectral anomalies. Certain wavelengths of light are dimmer than they should be, while others are unexpectedly brighter. This distinct pattern does not correspond to any known type of galaxy. Some researchers have wondered if the void's extreme emptiness might somehow alter the properties of light passing through it. But light does not change its nature simply by crossing empty space, unless that space possesses unusual characteristics of its own. This leads to the most unsettling discovery of all. The 60 galaxies are not oriented randomly. The axes around which they spin show a preference for similar directions, not a perfect alignment, but a correlation that is statistically impossible to be mere chance. It is as if they are all responding to the same vast, external influence. Galaxies form from collapsing clouds of gas that rotate in random directions, meaning their orientations should show no discernible pattern over cosmic distances. To find such an alignment suggests that a powerful force must have acted upon all of them at once, a force capable of either shaping their formation or altering their rotation long after they formed. We have no concept of what this force could be, as nothing in the standard model of physics is known to operate on such a monumental scale. And yet, the data confirming this alignment is robust, verified by multiple independent surveys. These 60 galaxies are more than just survivors in an empty realm. They are markers, pointing toward a phenomenon we have not yet discovered, something that arranged them, holds them in place, and has recently shown signs of becoming active. Galaxies, in a way, age much like living things. A young galaxy is a brilliant blue, ablaze with hot, massive stars that form quickly from a plentiful supply of gas. As the galaxy matures, its largest stars exhaust their fuel and die, leaving behind the cooler, redder stars that have longer lives. The galaxy's overall light shifts toward these longer wavelengths. In time, star formation dwindles and eventually ceases altogether. The galaxy transforms into a red, quiescent elliptical system, populated by ancient stars. This entire life cycle unfolds over billions of years. By examining the spectrum of a galaxy's light, one can read its history. Blue light signifies the ongoing birth of young stars, while red light indicates a much older population of stars formed long ago. The ratio between them tells the story of its age. The 60 galaxies in the Boötes Void are overwhelmingly red. Their spectra are dominated by light from stars that are 10 to 12 billion years old. These are systems that concluded their era of star formation billions of years in the past and have been quietly coasting through cosmic time ever since. They are, in essence, retirement communities for stars. Herein lies the central problem. Galaxies of this type are forged in dense environments. When numerous galaxies are packed together in a cluster, their combined gravity heats the intergalactic gas to millions of degrees. This superheated gas is unable to cool and collapse to create new stars, effectively shutting down star formation. the galaxies in the cluster age quickly and turn red. Voids represent the opposite conditions: low density, cold gas, and very few interactions between galaxies. Such an environment should encourage continued star formation, producing young, blue galaxies, not ancient red ones. So the question returns: how did these old elliptical galaxies arrive in the most desolate region of space? The conventional explanation would be that they formed in a dense cluster elsewhere and were later ejected, migrating into the void. While galactic migration does occur through gravitational interactions, the mathematics for this scenario do not add up. To get to the heart of the void from the nearest cluster, these galaxies would have had to travel between 50 and 100 million light-years. At the typical speeds of galaxies, such a journey would require several billion years. Over that vast timescale, they would have passed through regions containing fresh gas, which would have reignited star formation. They would not have remained purely red, and yet they are. There are no signs of recent star birth, no mixture of young blue stars. This suggests they aged where they are now, not during a long transit. An alternative idea is that these galaxies formed inside the void long ago, when the region was younger and denser. Before dark energy expanded the void to its current size, there might have been enough matter to build these mature galaxies. Then, the void grew around them, leaving them isolated. This theory, however, runs into problems with timing. The void would have needed to expand very rapidly just after the galaxies finished forming, and before any new gas clouds could give rise to younger galaxies nearby. The sequence of events requires a level of cosmic coordination that seems highly improbable. Others propose that the galaxies formed normally in a cluster, but were then transported into the void by some unknown force, a force that moved them quickly enough to preserve their ancient stellar populations. But what kind of force can move entire galaxies across cosmic distances without leaving any other trace? No such mechanism is known to exist. The final and most profound possibility is that these galaxies did not age naturally at all. Perhaps something within the void itself accelerated their evolution, a process or a field that caused time to pass more quickly in their local vicinity, making their stars live and die at a faster rate. The galaxies would appear old, simply because they have experienced more time than the universe has technically allowed. This explanation may sound like science fiction, but the flow of time is not constant. General relativity allows for time dilation under specific conditions, such as near the immense gravitational fields of black holes, or within the fabric of expanding space influenced by dark energy. Could the unique environment of the void somehow create those very conditions? The question arises whether its profound emptiness could warp the fabric of space-time itself, perhaps altering how time flows within its boundaries. While no direct evidence supports this idea, we currently lack a more satisfying explanation for the unusual appearance of these galaxies. If time were to pass differently inside this void, it might account for the signals that have been detected, patterns that repeat with the regularity of a clock, hinting that something within operates on a temporal rhythm separate from the rest of the universe. It suggests a countdown to an event that we are entirely unable to foresee. 3 years ago, astronomers directed the instruments of the Hubble Space Telescope toward one of the 60 void galaxies. Their goal was a routine observation, intended to measure the galaxy's stellar populations. What they recorded instead was something entirely unexpected. The galaxy faded. Over a span of 6 hours, its total light output diminished by 8%, and then it gradually returned to its normal level of brightness. This change was not abrupt. It occurred smoothly, tracing a curve similar to that of an eclipse, as if an object had passed between the galaxy and our point of view, obstructing the light. The research team initially concluded they had witnessed a random occultation, perhaps an object in the foreground that had drifted into their line of sight. Consequently, they marked the observation as potentially compromised and continued with their work. 2 months later, the very same galaxy faded once more. The magnitude of the dimming was identical, the duration was the same, and the shape of the light curve matched perfectly. This was no longer a random occurrence. It was clearly periodic. In response, the astronomers broadened their investigation to encompass all 60 of the void galaxies. They established monitoring programs that utilized multiple telescopes, enabling them to watch the region continuously for weeks at a time. Their findings sent a wave of unease throughout the astronomy community. It turned out that 17 of the 60 galaxies were exhibiting these dimming events. These events were not simultaneous, nor were they random. They adhered to a strict pattern. Galaxy A would dim, and then 3 days later, Galaxy B would follow. After another 5 days, Galaxy C would dim. This precise sequence would repeat every 78 days with unwavering regularity. Here were 17 galaxies, blinking in a specific, unvarying order. There is no known natural phenomenon that could produce this kind of behavior. Eclipses are random events, governed by the mechanics of orbits. Variable stars have their own independent pulsation cycles. Clouds of dust drift through space without any such coordination. It seems impossible for 17 galaxies, separated by millions of light-years, to dim in a synchronized sequence unless some force or object connects them. The nature of the dimming itself is also highly unusual. While an 8% loss of light might seem minor, it would require an object of enormous size to block that much illumination from an entire galaxy. This is not the eclipse of a single star we are considering. It is the collective light of the whole galaxy that is fading. Any obscuring object would have to be larger than the galaxy itself, stretching for hundreds of thousands of light-years across its diameter. Nothing of that scale is known to exist within the void. The region is, by its very definition, empty. Even if one could somehow combine all 60 of the void's galaxies into one single object, it would still not be massive enough to obscure 8% of the light from another galaxy. One alternative theory posits that the obstruction is not a solid body at all. Some researchers have proposed that what we are observing are interference patterns created by waves of dark matter propagating through the void. Dark matter is thought to be able to clump and flow, much like an invisible ocean. If waves were to travel through this region in a sequence, they could gravitationally lens the light from the background galaxies, thereby creating the dimming effect. This theory, however, requires dark matter to behave in ways that have never been observed, forming coordinated waves across millions of light-years and maintaining perfect timing for years on end without losing cohesion. While it is a possibility, it pushes our current understanding of dark matter to its absolute limit. Another hypothesis ventures into the realm of megastructures, vast, artificial constructions created by a highly advanced civilization. If intelligent beings had engineered enormous arrays of objects in specific orbits, they could indeed produce periodic dimming events. This explanation is compelling for those searching for techno-signatures. The pattern appears too precise, too deliberate to be natural, but it would necessitate a civilization with engineering capabilities that dwarf anything humanity can even imagine. It also raises the question of motive. Why would anyone build something designed to make galaxies fade? And what purpose could it possibly serve? The most troubling interpretation, however, is that the dimming is caused by something moving through the void itself, an entity or phenomenon that passes in front of each galaxy in sequence, temporarily blocking its light. This would mean something so vast it can eclipse entire galaxies. It would be something following a calculated path that brings it near each of the 17 affected galaxies in a specific order. If this is what is truly happening, then we are witnessing something of incomprehensible scale, traveling through the emptiest part of space. It is something that operates on a schedule we can now predict, and something that will eventually complete its current circuit only to begin it once more. The next dimming event is scheduled to occur just 3 days from now. Telescopes across the globe are already aimed at the target galaxy. Whatever unfolds, We will be watching, waiting to see if the pattern holds true, waiting for some clue to understand what is casting these immense shadows, and hoping that it never directs its attention toward us. Radio telescopes are now scanning the void constantly. Following the discoveries of the dimming galaxies, astronomers came to realize they had been overlooking a vast, empty region that might hold unprecedented phenomena. They aimed their instruments into the darkness between the 60 galaxies and began to listen. What they found was that the void is not silent. In 2022, the Very Large Array in New Mexico picked up radio emissions originating from deep within the void's interior. The signals were not coming from any of the 60 galaxies, but from the empty space between them. The signal manifested at a frequency of 1.4 gigahertz, which is often used in radio astronomy for its ability to cut through cosmic interference. This emission continued for 43 minutes and then ceased. 2 weeks later, it appeared again from the same location, at the same frequency, and for the same duration. Over months of observation, a clear pattern emerged. The signal broadcasts every 14 days, with a precision that varies by less than 3 minutes. Radio emissions coming from empty space are a deep puzzle. Radio waves require a source. Stars produce them, as do gas clouds and black holes that are actively consuming matter. But a vacuum should produce nothing. Yet here was a signal that seemed to originate from a region where our instruments show no matter at all. The signal itself also possesses a complex structure. It is not simple static or a series of basic pulses. Its intensity fluctuates in a manner that suggests modulation, as if information is being encoded into the broadcast. Scientific teams have subjected the signal to every known analysis technique, searching for patterns that could point to either a natural origin or an artificial intelligence. Natural pulsars do create regular radio signals, but they achieve this by rotating, which causes their beams to sweep past Earth periodically. This signal, however, does not sweep. It simply appears and then disappears without any sign of rotation. Other phenomena, like rotating radio transients, flash randomly, not on a perfect 14-day schedule. While magnetars are known to generate radio bursts during powerful stellar quakes, those phenomena are characterized by their violence and irregularity. The source being observed displays none of these traits. It broadcasts with a serene regularity, transmitting for a period of 43 minutes before falling completely silent. This pattern of behavior is more reminiscent of an artificial station than any known natural object in the cosmos. The location of the signal adds another layer to the enigma. It seems to emanate from a point approximately 60 million light-years deep inside the void. This position is notably equidistant from 3 of the galaxies that have been observed dimming. A distinct geometric relationship is formed by its placement relative to these galaxies. It does not appear random or coincidental, but rather deliberately situated. When scientists created a map plotting the dimming galaxies and the radio source together, a shocking picture emerged. Their positions create a 3-dimensional lattice, a true structure. The galaxies occupy specific points within this framework, and the radio source sits at a central node. This entire configuration spans a vast 100 million light-years, yet it maintains these precise geometric connections. Natural cosmic structures simply do not assemble into lattices. Galaxies are known to cluster under the influence of gravity, which results in irregular clumps and long filaments. They do not organize themselves into geometric patterns unless an external force has intentionally arranged them. The 14-day cycle of the broadcast aligns perfectly with 1/3 of the dimming event cycle. While this could be a coincidence, the mathematical precision feels intentional. It suggests the radio source and the dimming events are somehow coordinated, perhaps serving interconnected functions. Some scientists have put forward the idea that we are detecting an automated beacon. This could be an ancient transmission left behind by a civilization that vanished long ago, broadcasting a message into the void for millions or even billions of years. If so, It is a message that no one has been present to receive until this moment. The potential age of such a beacon is staggering. The void itself is billions of years old. For any signal to broadcast for that duration would necessitate technology far beyond our current understanding. It would require self-repairing systems, power sources that are effectively inexhaustible, and an engineering resilience that could outlast the stars themselves. An alternative view suggests the signal is not ancient at all, but quite recent. This theory posits that something new has activated within the void. It proposes something began its broadcast only within the last several years. This timing is troubling for astronomers. It implies that the fundamental properties of the void are changing right now, during the very brief window in which humans are capable of observing them. One must wonder about the odds that we would develop intelligence at the exact moment the void started to unveil its secrets. Either humanity is incredibly fortunate, or the void is reacting to an external stimulus. Perhaps it is a response to our own radio transmissions that have been leaking out into space. It could be reacting to the gravitational influence of our own galaxy as it journeys through the cosmos. Or it could be something else entirely. The most recent observations indicate that the signal's strength is on the rise. Each 14-day broadcast is received slightly louder than the one that preceded it. The rate of this growth is small, just 2% per cycle, but it is consistent. If we extrapolate this trend, the signal is projected to be 10 times stronger in only 5 years. What might happen when it finally reaches its full intensity? What is this process building toward? We are left with no answers. There is only a growing sense of concern that we may be witnessing the activation phase of something that has laid dormant for eons. Then, just last month, a second radio source was detected. The cosmic microwave background, or CMB, represents the most ancient light in our universe. It came into being 380,000 years after the Big Bang, at the moment when space had cooled sufficiently for atoms to form. Before that critical point in time, the universe was opaque. Light was unable to travel freely because it was constantly being scattered by charged particles. After that moment, however, light began to stream outward, carrying with it an image of the universe in its infancy. We can still observe this ancient light today. It reaches our instruments from all directions in the form of faint microwave radiation. Across the entire sky, the CMB appears almost perfectly uniform. Its temperature variations are minuscule, measuring only 1 part in 100,000. These tiny fluctuations were the seeds of all cosmic structure, mapping the density variations that would eventually grow into galaxies and voids. Yet, in one particular direction, there is an exception. When astronomers measured the CMB in the direction of the Boötes Void, they discovered something was amiss. The temperature in that specific region is lower than in the surrounding areas. The difference is not large, only a few millionths of a degree, but it is measurable, consistent, and real. This drop in temperature is explained by what is known as the integrated Sachs-Wolf effect. When light from the CMB passes through a void, it tends to lose energy. The reason for this is straightforward. As the light enters the void, it must climb out of the gravitational potential of the surrounding matter. This act of climbing requires energy, which slightly cools the light. As the light then exits the void on the other side, it falls back into the gravity of normal space, which should allow it to regain the energy it lost. Under normal circumstances, these two effects cancel each other out. The light cools upon entry and warms upon exit, resulting in a net change of 0. However, our universe is expanding. Dark energy is constantly stretching the fabric of space, while the light is in the process of crossing the void. If the void itself grows during the light's transit time, the exit point is deeper within the surrounding matter's gravitational field than the entry point was. Consequently, the light does not recover all of the energy it initially lost. It arrives at our detectors cooler than when it started its journey. This effect is typically very small, Most voids are expected to create temperature variations of only a few millionths of a degree. The Boötes Void, however, creates a cold spot that is 10 times larger than our models would predict. This discrepancy suggests one of two things. Either the void is expanding much more rapidly than other voids, or it began its existence far emptier than our theories predict. Neither of these explanations is fully satisfying. A faster expansion would require a stronger concentration of dark energy. But dark energy is understood to be distributed uniformly throughout space. It should not be concentrated in specific regions. The idea that it started emptier merely pushes the problem further back to the era of void formation. Why would this one region have been so much emptier than any other? Some cosmologists have proposed that we are observing evidence of primordial quantum fluctuations. In the very first moments after the Big Bang, quantum uncertainty is thought to have created slight variations in density. Most of these variations were small. Very rarely, a large fluctuation would have occurred. The Boötes Void might just represent an extreme statistical outlier. When you calculate the probability of such an event, you arrive at numbers like 1 inch, 10 million. It is highly unlikely, but not impossible. The universe is immense. Rare events are bound to happen somewhere. We could simply be witnessing the far tail of a probability distribution, but there are other observed effects that only amplify the mystery. The CMB cold spot is not circular. It is elongated and stretched, as if something has pulled on the void from a particular direction, distorting its shape. Voids are expected to expand symmetrically in all directions. This one appears to have grown asymmetrically. Something has influenced its pattern of growth. The elongation points toward a specific region of the sky. If you follow that direction outward, you pass through the void, through the galaxies that lie beyond it, and toward the very edge of the observable universe. The question remains whether this alignment has a deeper meaning. Is it possible that we are witnessing a link between the void and cosmic structures so remote they lie beyond our direct observation? Recent simulations have begun to point toward an entirely different explanation. If our own universe is not the only one, but part of a larger multiverse existing in higher dimensions, then collisions between these separate realities could leave behind permanent scars in the fabric of space. The sites of these impacts would likely appear as regions of exceptional emptiness. They would also affect the light of the cosmic microwave background, stretching its wavelengths as it passed through them along certain pathways. Such features would inherently conflict with our standard cosmological models, as their formation would be governed by physical processes external to our universe's own evolution. One must then ask if the Boötes Void could be such a scar, left by the collision of a parallel universe. The concept may seem extraordinary, yet it provides a better fit for the observations than more conventional theories. It manages to account for the profound emptiness, the staggering size, the asymmetrical geometry, and the anomalously large temperature drop in the background radiation. And if this idea holds true, it presents a deeply unsettling thought. If two universes did indeed collide in this location, does that connection persist? Is it conceivable that forces, or even entities, from that other cosmos could traverse the void and enter our own? Could the unusual signals being recorded actually have an origin beyond our known reality? On the map of the early universe, the cold spot seems to gaze back at us like a great eye. It is an ancient wound in space-time that has never quite healed, and now it shows signs of stirring. Light, as a general rule, travels in a straight line. This is a foundational concept, but it isn't the complete truth. The presence of mass fundamentally bends the geometry of space, and light has no choice but to follow these curves. This phenomenon, known as gravitational lensing, allows us to create maps of dark matter by observing how its gravity distorts the light from more distant objects. When light traverses a void, however, it should experience very little bending. Voids are defined by their minimal mass. Without significant mass, space remains relatively flat, allowing light to proceed on a straight path with barely any deflection. This characteristic is precisely what makes voids easy to pinpoint. They appear as blank areas where the effects of gravitational lensing all but disappear. The Boötes Void, however, does not conform to this expectation. Light that passes through it is bent incorrectly. It is not a powerful distortion, like one would see near a cluster of galaxies, but a subtle one. The effect is as if the void harbors some invisible mass that should not be there, or perhaps as if space itself possesses different properties inside the void than it does outside. This strange anomaly came to light while astronomers were charting the distribution of dark matter across the cosmos. Their method involves measuring how the light from faraway background galaxies is warped as it journeys through structures in the foreground. A greater degree of distortion implies more mass along that line of sight, while less distortion indicates less mass. When they directed their observations through the void, they anticipated finding only the most minimal distortion. What they found instead was a measurable lensing effect, subtle yet undeniably present, consistent and repeatable. The void contains something that bends light, even though all of our instruments indicate the region is empty. When one calculates the amount of mass required to generate this lensing, the answer is disturbing. The void would need to contain roughly 10% of the matter that would exist in an equivalent volume of normal space. This is not nothing, and it is far from the expected 1% of residual matter typically found in voids. A 10% matter density is sufficient to form thousands of galaxies. So where is all of this matter? We are unable to see it in visible light. Our radio telescopes cannot detect it. Observations in the X-ray spectrum reveal nothing. It remains invisible across the entire range of electromagnetic radiation. And yet, it gravitationally lenses the light from behind it, which serves as proof of its existence. Dark matter can explain some of this discrepancy. While dark matter does not emit light, it does possess mass, and therefore creates gravitational lensing. Every part of space, including voids, contains some amount of dark matter. It's possible the Boötes Void simply held on to more of its dark matter than is typical when its ordinary matter was evacuated. However, dark matter and regular matter are generally coupled by gravity and tend to move together. As regular matter departs from a void, dark matter is expected to follow. To find a concentration of dark matter without its regular counterpart would require a mechanism to break that gravitational bond, and we currently know of no such process. An alternative possibility is that our measurements are somehow being misinterpreted. Perhaps light is being bent for reasons that are not related to mass at all. Certain modified gravity theories propose that on cosmic scales, gravity might operate differently than our current models predict. If such theories proved correct, the strange lensing could be a consequence of altered gravitational laws within the void itself. To test this idea, we would need to compare lensing measurements from a multitude of void regions. Do all large voids exhibit similar anomalies? Or is this quality unique to the Boötes Void? Initial surveys suggest that the Boötes Void is indeed unusual. Other voids seem to produce the minimal lensing that theory predicts. This one appears to be an exception. The lensing pattern itself also displays a certain structure. It is not uniform across the entire expanse of the void. Some lines of sight passing through it reveal stronger lensing, while others show weaker effects. When these variations are mapped out, distinct patterns emerge. There appear to be concentrations of whatever is responsible for bending the light. Intriguingly, these concentrations align with the locations of the 60 known galaxies and the mysterious radio source, as if an invisible network resides within the void. This suggests the presence of unseen filaments connecting the galaxies to one another and to the radio source. These filaments would have to contain enough mass to lens light, yet somehow remain completely undetectable by our instruments. What kind of substance could behave this way? Ordinary matter either emits light or, at the very least, absorbs and blocks it. dark matter interacts only through the force of gravity. This hypothetical network would have to be composed of something else entirely, perhaps a third type of matter we have yet to discover, or a form of energy structured in a way we do not yet comprehend. The latest generation of gravitational wave detectors may provide new clues. If massive objects were moving within the void, they would generate ripples in space-time itself. These ripples would then propagate outward at the speed of light as gravitational waves, which could be detected by sufficiently sensitive instruments. Several research teams are now actively monitoring the region of the void for any such gravitational wave signals. They are searching for periodic patterns that might match the 14-day cycle of the radio broadcast or the 78-day dimming cycle of the star. Any correlation would be definitive proof that something massive is in motion inside the void, something tangible enough to warp space-time, yet invisible to all our senses except gravity. So far, no signals have been found, but the sensitivity of their equipment improves with each passing month. And a new question has begun to surface. Is whatever resides inside the void moving toward us? Or are we, as our galaxy drifts through intergalactic space, moving toward it? This question arises because the lensing anomalies are gradually becoming stronger. Year by year, light passing through the void bends just a little bit more. It suggests that whatever is in there is either growing, activating, or somehow consolidating its presence, and we still cannot see what is coming. Dark matter is what built the cosmos we see today. It outweighs all regular matter by a ratio of 5-to-1. Without its gravitational influence, galaxies would have flown apart long ago, and the vast cosmic structures that define our universe would never have had a chance to form. Dark matter acts as a gravitational anchor, clumping around galaxies and holding them together. Dark matter sculpts the universe on the grandest of scales, creating enormous halos that extend far beyond the luminous boundaries of galaxies. It weaves through space as immense filaments, giving rise to the structure known as the cosmic web. We find its influence almost everywhere we direct our attention, as it represents the dominant portion of the cosmos's mass budget. And yet, within the Boötes Void, the dark matter seems to be missing. According to theoretical predictions, cosmic voids are expected to hold onto about 15 to 20% of the dark matter they initially contained. As regular matter is evacuated during a void's formation, much of the dark matter leaves as well, but never all of it. The pull of gravity is simply not powerful enough to sweep a region completely clean of dark matter, meaning some should invariably be left behind. However, numerous surveys that have mapped the dark matter distribution in the Boötes Void, using techniques like gravitational lensing and studies of galaxy velocities, have revealed a startling discrepancy. These studies found that less than 5% of the anticipated dark matter content is present. An astonishing 75% of the dark matter that ought to be there has simply vanished. Within the framework of standard physics, this outcome is considered impossible. Dark matter's only known interaction is through gravity. It is unable to radiate away energy. It cannot exert pressure to push itself apart, and it cannot escape a region unless acted upon by some other force. We are not aware of any force that could be capable of ejecting dark matter from such a colossal volume of space. Some physicists have explored the idea that dark matter might interact with itself more than we have assumed. Perhaps dark matter particles engage in rare collisions with one another, transferring momentum in the process. Over vast stretches of time, these infrequent interactions could potentially clear dark matter from voids more effectively than gravity could alone. But when this concept is tested with models, it proves unworkable. The self-interactions would need to be so strong to fully clear the void that they would generate other observable phenomena that we do not detect, causing the hypothesis to fail. Other theories suggest the void may have formed in an unusual way. It might have originated from a region with far less dark matter than the cosmic average, a primordial underdensity that has endured since the Big Bang. This explanation, however, would necessitate an extreme fine-tuning of the universe's initial conditions, a scenario that is possible but so statistically improbable that it borders on the absurd. A third possibility is that some unknown agent removed the dark matter after the void had already taken shape, as if something passed through this area and swept it clean. The question then becomes, what could possess the power to influence dark matter on such a monumental scale? Dark matter interacts so weakly with anything that it passes through ordinary matter as if it were a ghost. Displacing it would require forces to which we have no access. This line of inquiry leads to a more speculative notion, that the void might be connected to something beyond our own space-time. If higher dimensions exist, it is conceivable that dark matter could, under specific circumstances, leak into them. The extreme emptiness of the void could potentially create a weakness in the dimensional barrier, allowing dark matter to drain away into other universes and leaving our own space depleted. While this sounds like a concept from the frontiers of theoretical physics, and indeed it is, the observations themselves compel us to consider explanations that lie outside the standard model. We are forced to entertain possibilities that would normally be dismissed. The distribution of the little dark matter that does remain is just as perplexing. Rather than being spread out uniformly throughout the void, it is gathered into very specific locations. These are the same locations where we have observed anomalous gravitational lensing, and they align perfectly with the 60 galaxies and the mysterious radio source. It is as if some force is actively collecting the dark matter, gathering it from the emptiness, and concentrating it in particular spots for purposes we cannot begin to comprehend. Recent computer simulations have attempted to model the consequences of removing most of the dark matter from a cosmic void. The outcomes were dramatic. Without the gravitational scaffolding that dark matter provides, the remaining ordinary matter grows unstable. Galaxies that should be in peaceful orbits begin to display chaotic movements. The very structure of the void should either collapse or fly apart. But the Boötes Void remains stable. Its 60 galaxies maintain their positions, and the geometric lattice persists, all without the dark matter foundation that should be supporting it. This implies that something else is supplying the necessary stability, taking over the gravitational role that dark matter would normally play. A handful of researchers have dared to suggest that the void is not truly empty. Instead, it is filled with something we are not yet able to detect, a form of matter or energy that interacts gravitationally with both normal and dark matter, but is otherwise invisible to all our current instruments. This hypothetical substance would need to be even more weakly interacting than dark matter itself, a shadow of a shadow. Whether we call it dark matter or phantom energy is less important than what its existence would mean. It could resolve multiple puzzles at once, explaining the missing dark matter, the strange lensing, the stability of the galaxies, and the geometric formations we see. But it also suggests the void is not empty at all. It is full, brimming with an ocean of something our senses are only just beginning to grasp, and that ocean seems to be stirring. We can almost perceive its currents now in the changing lensing patterns and the shifting gravitational fields, like a vast entity awakening from a sleep that has lasted for eons. It is as if something ancient has taken notice of our observations and has chosen to respond. The question is no longer about what happened to the dark matter. The question has become what took it, and whether it intends to take more. The void possesses boundaries, and they are remarkably sharp. On one side, galaxies cluster together in walls and filaments, shining with the light of trillions of stars. On the other side, there is only emptiness. This transition occurs abruptly, over a distance of just 10 to 20 million light-years, creating a kind of cosmic cliff where the universe seems to drop off into nothingness. The physics governing these boundary regions should be predictable. Galaxies near the edge experience gravitational forces from two directions. The wall of galaxies behind them exerts a backward pull, while the empty void ahead offers a minimal forward pull. The net effect should be a slow drift of these galaxies toward the walls, away from the void. Over cosmic time, the void should gradually shrink as galaxies crowd inward around its edges. But that is not what is happening. The galaxies at the boundary are not moving toward the walls. Some appear to be stationary, while others are actually moving toward the void, flowing backward into the emptiness. Astronomers made this discovery by measuring the red shifts of these galaxies. A galaxy's red shift reveals how quickly it is moving toward or away from Earth, and by comparing many galaxies in a region, a map of their collective motion can be created. In most cosmic structures, galaxies are observed falling toward regions of higher density, drawn by gravity. The edge of the void shows the opposite. Galaxies are falling toward a region of lower density, toward the emptiness. This behavior violates fundamental physical laws, unless something inside the void is pulling them inward. When one calculates the gravitational force necessary to reverse the motion of these galaxies, the result points to an enormous amount of mass, more mass than is contained in all 60 of the void's galaxies, and more mass than in any structure we can currently detect. It suggests an invisible concentration of mass, lurking somewhere in the void's deep interior. The gravitational influence here is powerful enough to overcome the pull of surrounding galactic walls. The source of this immense mass, however, remains a profound mystery, as we have no clear answers about its location or its composition. While dark matter might seem like a plausible candidate, observations have established that the void is actually deficient in it, not abundant. And since ordinary matter is visible, and we detect virtually none, the void would have to be filled with a vast quantity of some entirely new, undiscovered substance. What stands out is that this gravitational pull is not evenly distributed around the void's perimeter. Instead, it concentrates intensely in 3 specific areas, which remarkably form the vertices of a perfect equilateral triangle. From our perspective on Earth, the center of this triangle aligns with the position of the radio source, and each of its 3 points corresponds to one of the dimming galaxies. This recurrence of geometry hints at a level of organization that challenges the idea of natural, random cosmic formations. Such patterns are often unsettling for astronomers, as they point toward either an extraordinary coincidence or some form of deliberate construction, and neither explanation is easily accepted. Continuous monitoring of the galaxies along the void's edge reveals a crucial detail. By tracking their positions year after year, scientists have found that these galaxies are accelerating. They are not merely drifting inward. Their velocity is increasing, which suggests that the force drawing them in is actually growing stronger over time. If we project these acceleration curves into the future, several of these border galaxies are on a course to enter the void within the next million years. Upon crossing that threshold, they would likely be integrated into the geometric lattice, joining the 60 galaxies already suspended within that mysterious internal network. This raises a compelling question. Is the void actively feeding, growing by collecting material from its cosmic neighborhood? The standard model of cosmology suggests voids should expand and push matter outward. This one, however, appears to be doing the exact opposite, pulling matter inward in a way that defies our expectations. One hypothesis put forward by theorists is that we might be witnessing the formation of a cosmic string. These are theoretical imperfections in the fabric of space-time, thought to be remnants from the Big Bang. Though thinner than an atom, they would possess an immense gravitational pull. The presence of a cosmic string traversing the void could account for the gravitational anomalies we see. The challenge for this theory, however, is that such an object should be detectable through its gravitational lensing effect, bending the light from more distant objects in a characteristic manner. Despite numerous surveys looking for this specific signature in the region of the void, nothing has been found. If a string is there, it remains inexplicably hidden from view. An alternative explanation centers on the concept of frame dragging, a prediction of Einstein's general relativity, where a rotating mass literally drags space-time along with it. While this effect is typically minuscule and measurable only near objects like rapidly spinning black holes, a truly colossal rotating mass inside the void could potentially drag space-time on a much grander scale. But what could be rotating within an otherwise empty expanse? No known natural object possesses coherent rotation across hundreds of millions of light-years. That kind of synchronized movement would seem to require coordination, purpose, or even engineering. The latest data on this mystery come from gravitational wave detectors, instruments designed to sense the ripples in space-time generated by accelerating masses. Thus far, they have not registered any distinct waves originating from the void itself. Yet they have uncovered something just as puzzling. When aimed at the void, these sensitive detectors register a persistent noise, not random static, but a structured, low-frequency hum that lingers just below the official threshold for a confirmed signal. Though it is too faint to be definitively classified, it is remarkably consistent, always present, at the same frequency and from the same direction in space. While instrument error is a possibility, that explanation is challenged by the fact that every detector exhibits the identical noise pattern. Observatories in Louisiana, Washington, Italy, and Japan all register this same hum when they are oriented toward the void, making a simple coincidence highly improbable. One might wonder if this is the sound of space-time itself resonating, as if the void were an immense cavity amplifying specific gravitational frequencies. Or perhaps we are detecting the heartbeat of something else, a colossal object pulsing in the dark, its rhythm too slow for our direct perception but steady enough to generate constant vibrations in the very fabric of reality. The frequency of this hum translates to a cycle, with a period of about 2 years. If this phenomenon is genuine, it means we have already observed it through 3 complete cycles. Calculations predict the next peak in this cycle will occur in 9 months, at which point every gravitational wave observatory on the planet will be focused on the void. The result will either confirm the signal's existence or reveal it as an instrumental artifact. Yet there is a quiet sense among many researchers that they know what they will find, that the hum is real, that the void is communicating in some way, and that we are on the verge of understanding its message. The Big Bang was far from a uniform event. The universe's first moments were a time of violent, chaotic, and transformative change. Space itself inflated at speeds exceeding that of light, while quantum fluctuations were stretched to cosmic proportions and phase transitions tore through reality. According to some cosmologists, these transitions may have left behind scars, places where the fabric of space-time was damaged and never fully repaired. These cosmic wounds could persist to this day as the unusual structures we now observe. It is possible that voids are these very scars, regions where a phase transition unfolded imperfectly, giving rise to zones of lower density that eventually expanded into the vast empty spaces we chart today. Most such voids would likely be minor defects, but on rare occasions, a more significant rupture could have occurred, a wound deep enough to form something on the scale of the Boötes Void. This hypothesis leads to several testable predictions. First, voids formed this way should have irregular shapes. While voids formed through natural processes tend to be symmetrical, a wounded void would reflect the geometry of the initial tear, resulting in elongation or asymmetry. The Boötes Void is indeed asymmetric, and its distinctly elongated shape is consistent with what this theory predicts. A second prediction is that cosmic wounds would leave a specific imprint on the cosmic microwave background, meaning the associated cold spot would exhibit features more complex than simple cooling. The CMB cold spot corresponding to the Boötes Void displays exactly these kinds of features, containing intricate sub-patterns that are not observed in ordinary voids. A third consequence of this theory is that if these voids are wounds, they might still be bleeding energy or particles into the space around them. This would manifest as detectable anomalies near the void's boundaries, such as excess heat. In fact, infrared surveys of the regions bordering the void have revealed temperatures that are slightly elevated when compared to the edges of other, more typical voids. The temperature difference is subtle, only a few degrees, but it is both measurable and consistent. The theory, it seems, is on solid ground. Yet it also makes another, more profound prediction. If voids are truly wounds left over from the early universe, then they ought to contain relics from that time. These would be remnants of the physical conditions that prevailed during the Big Bang. Such artifacts would be exotic objects or fields that could not form in the cosmos as it exists today. They would represent a form of physics from an era when the universe operated under a different set of rules. The discovery of these relics would undoubtedly revolutionize physics. It would provide us with direct evidence of the universe's very first moments. This would allow us to test our foundational theories of cosmic inflation and phase transitions. It is even possible that new fundamental forces or particles could be revealed. This raises a compelling question. Could the signals emanating from the Boötes Void be these very relics? Could the radio broadcasts and the dimming events be manifestations of ancient physics still active inside a cosmic scar? The timeline is certainly a match. The wound itself would have formed 13 billion years ago, and any relics would have been trapped inside it ever since. We are only just now creating instruments with the sensitivity required to perceive their activity. Some scientists take this concept even further. They have proposed that the void is not merely leaking energy, but is instead leaking information about structure itself. The geometric lattice we can observe might be an imprint from a higher dimensional physics, bleeding through this wound in space-time. It would be analogous to viewing a shadow cast by a reality we cannot otherwise perceive. If this were true, we would be witnessing something that transcends the normal physics of our universe. It could be a window into the higher dimensional space that envelops our cosmos, or perhaps into the quantum foam that underpins space-time, or even into the symmetry-breaking events that define the period of cosmic inflation. Any one of these possibilities would rewrite our textbooks. They would transform the void from a simple astronomical curiosity into a laboratory for fundamental physics. It would be a natural experiment, revealing the deepest workings of the universe. There is, however, a darker interpretation. A wound can become infected. If the void is a tear in the fabric of reality, then it is conceivable that something from the outside could have entered through it. The signals we are detecting might not be remnants of the Big Bang at all. They could be evidence of an intrusion, something from another universe, or a different dimension that is using the wound as an entry point. This explanation aligns with the available observations with an uncomfortable degree of precision. It would account for why the void appears to be more active now than it was in the past. The wound could be widening, allowing the intrusion to grow. What may have begun as a small defect billions of years ago could have expanded into a route for an invasion. We might be observing the initial stages of a cross-dimensional incursion. In this scenario, the radio signals could be a form of communication between these intruding entities. The dimming events might be their construction projects. The gravitational anomalies could be the effects of their machinery altering the local space-time. The majority of scientists dismiss this interpretation as belonging to the realm of science fiction, but a small number of researchers take it seriously. They argue that we have no prior experience with cosmic wounds or higher dimensions. Our intuition about what is possible or impossible is simply not applicable here. We have a responsibility to consider every explanation that fits the data, regardless of how unsettling it might make us feel. The essential difference between a remnant and an intruder is intent. Remnants are passive. They exist, but they do not act. Intruders are active. They expand, they build, and they alter their environment to suit their purposes. The Boötes Void is exhibiting all of these behaviors. It is changing, expanding, and building geometric structures, while its activity increases year by year. This is the behavior of an intruder, not a remnant. And if something is indeed invading our reality through the void, we must learn what it wants. We need to understand why it is organizing matter into lattices, why it is broadcasting signals, and why it is collecting galaxies. We must find these answers before it can finish whatever it is building. This is because the construction appears to be nearing completion. The geometric patterns are now almost perfect. Only a few more galaxies need to fall into place, and a few more years of radio broadcasts may be all that is left. Then, the structure will be finished. And what happens then? What occurs when an invading force from beyond our reality completes its construction inside a cosmic wound? What new capability will that grant them? What will they be able to do that they could not do before? We are on the verge of finding out. A countdown has effectively begun. The structure is expected to be complete within a decade, perhaps even sooner. At that point, we will learn whether we have discovered a fascinating astronomical phenomenon or a threat to our very existence. Voids are known to grow over time. The force of dark energy pushes their boundaries outward, evacuating more matter and creating ever larger regions of emptiness. This expansion is an exceptionally slow process. Voids typically increase their size by about 1% every billion years. If you were to measure a void's size today and return in 100 million years, you would barely be able to notice the difference. The Boötes Void, however, is growing faster. It is growing much, much faster. An analysis of historical astronomical data indicates the void's diameter has increased by nearly 2% in just the last 50 years. That rate is 10,000 times faster than our predictions allow. How can we know this? Astronomers measure the sizes of voids by mapping the distribution of galaxies around them. The edge of a void is found where the galaxies stop appearing. By comparing maps from different years, it is possible to track the expansion. Early surveys from the 1,980 seconds placed the void's diameter at 320 million light-years. Modern surveys now put it at 330 million light-years. That is 10 million light-years of growth in just over 4 decades of human observation. This should be impossible. The expansion of a void is dependent on the strength of dark energy, which is understood to be constant throughout space and time. You cannot suddenly accelerate the growth of a single void without changing the properties of dark energy. And if the properties of dark energy had changed, we would detect that change everywhere, not just in one specific void. Yet the Boötes Void expands at this anomalous rate. Something localized to the void is driving this accelerated expansion, something that pushes its boundaries outward faster than dark energy alone can explain. This expansion is also not uniform. Different edges of the void are growing at different rates. The side that is facing toward the location of the radio source is expanding the fastest. The opposite side is expanding the slowest. The void is stretching in a specific direction, becoming more elongated with each passing year. This directional growth implies the presence of a force gradient. It is like a pressure wave propagating outward from a central point, or like an explosion expanding through space. But a normal explosion slows down over time as its energy dissipates. This expansion is accelerating year by year. The rate of growth is itself increasing. The void is expanding faster now than it was a decade ago. If we project this forward, the rate of expansion will be even greater 10 years from now. At the current pace of acceleration, the void is on track to double its size in a mere 2 million years, which on cosmic timescales is practically instantaneous. Structures that ordinarily require billions of years to evolve will experience profound transformations in a fraction of that time. This raises a critical question about the 60 galaxies located inside. What happens to them when the void doubles? Do they simply spread out, preserving their geometric pattern across a much larger volume of space? Or does the expansion instead compress them, forcing them closer together toward an eventual collision? Computer simulations suggest that neither of these simple outcomes is stable. The models indicate the galaxies should either be flung apart entirely, dispersing into the cosmos, or they should coalesce into a single, massive, gravitationally bound structure. Both of these processes would normally unfold over hundreds of millions of years. However, if the void expands as rapidly as observed, these cosmic events could happen in just a few million years. It is as if we are observing a colossal collision in extreme slow motion, a pace that seems slow from our perspective, but is incredibly fast by astronomical standards. It may be that the 60 galaxies, arranged in their peculiar lattice, are already falling toward a common center. In a million years, they could meet, and when they do, the resulting release of energy would be visible across the entire observable universe. This outcome is not certain. However, if something is preventing the collision, or if the geometric arrangement is not a random placement, but a carefully balanced structure, one might imagine it like balls on a warped pool table, held in specific spots where the table's curvature keeps them stationary. The void's expansion could be generating a unique geometry in spacetime that holds the galaxies in place, despite the powerful forces attempting to move them. Such a scenario would require exotic physics. A curvature in spacetime strong enough to balance the motion of galaxies exceeds what can be produced by normal matter. You would need immense gravitational fields, perhaps from black holes or something even denser. A recent clue has emerged from new observations. Stars at the outer edges of the 60 void galaxies exhibit unusual velocities. They are orbiting the centers of their galaxies faster than would be expected based on the visible matter alone. This is the classic signature of dark matter, the invisible mass that provides the extra gravity needed to hold galaxies together. What is particularly intriguing, however, is that the rotation of these void galaxies is excessive, even more than what dark matter can typically provide. It is as if they contain enormous concentrations of some other missing mass, enough to dwarf the visible stars and gas by factors of hundreds or even thousands. The puzzle is where this mass could be hiding. Regular matter glows, dark matter does not, but it reveals itself through its gravitational effects on visible matter. This hypothetical excess mass does neither. It must have collapsed into extremely compact forms. Black holes are the most obvious candidates, but black holes of that magnitude would emit X-rays as they consume surrounding gas, and we detect no such X-ray emissions. The mass remains dark, even to our most sensitive indirect detection methods. Some physicists have proposed the existence of primordial black holes. These are not the remnants of collapsed stars, but black holes that could have formed in the first second after the Big Bang, when density fluctuations were extreme enough for regions of space to collapse directly without first forming stars. Primordial black holes could possess any mass, and they would not emit X-rays if nothing were falling into them. They would be perfectly invisible, detectable only through their gravity. If the void galaxies do contain swarms of primordial black holes, that could explain their excessive rotation curves. It would also explain the anomalous gravitational lensing that has been observed, and it could even provide a mechanism for the void's accelerated expansion. Black holes warp spacetime, and many of them close together could create complex spacetime geometries. These geometries might be able to channel dark energy more efficiently than flat space does, which would effectively amplify dark energy's push and accelerate the void's growth. While this idea is speculative, it presents a cohesive picture. The void contains hidden black holes. These black holes drive the accelerated expansion. The expansion pulls more galaxies inward, and these galaxies bring more black holes, creating a self-reinforcing cycle. If this cycle continues unchecked, the void will continue to grow. It would eventually consume the surrounding galaxy walls and merge with adjacent voids. Over time, it could become so large that it would affect cosmic structure on the grandest scales. The universe's delicate web of galaxies and voids would destabilize, and its evolution would diverge from current predictions. The Boötes Void might be giving us a preview of our universe's own distant future, a glimpse of what happens when dark energy wins its battle against gravity decisively. This is a future where voids expand until they swallow everything, and the cosmos becomes a collection of isolated galaxy groups separated by ever-growing gulfs of emptiness. Or perhaps it is not the far future, but the near future. If the void's growth continues to accelerate, we might witness dramatic changes within human lifetimes. The expansion could eventually reach Earth's region of space, and our own galaxy might begin to feel its effects. Our sky might darken as nearby galaxies flee into the growing emptiness. We have a front row seat to something unprecedented, an event that should not happen for trillions of years but is happening now, and we still do not know why. Galaxies do not exist in isolation. They cluster into groups, drawn together by their mutual gravity. Between these clusters, vast empty spaces separate one group from the next, which is the standard picture of cosmic structure. The 60 void galaxies should be isolated, separated by tens of millions of light-years of empty space and far too distant to interact gravitationally. Each galaxy should be orbiting alone through the void, independent and disconnected. New observations, however, reveal otherwise. Deep radio imaging has shown faint filaments connecting the galaxies, which appear as thin threads of material spanning the gaps between them. These filaments are barely visible, thousands of times fainter than the galaxies themselves, but their existence is undeniable and real. The light they emit is synchrotron radiation, a type of light formed when charged particles spiral through magnetic fields at nearly the speed of light. The emission spectrum tells us the particles are electrons, and that the magnetic fields are surprisingly strong, even stronger than the magnetic fields found between normal galaxy groups. The question is where these particles come from. Galaxies constantly expel material through stellar winds and supernova explosions, and this gas flows outward into intergalactic space. Normally, it disperses and becomes undetectable within a few million light-years. The void filaments, however, extend for 50 million light-years or more. Something is channeling and focusing the gas, preventing it from dispersing. Strong magnetic fields could achieve this, as they are known to constrain charged particles, forcing them to flow along invisible field lines. The particles, it was thought, would trace the invisible pathways of magnetic fields, flowing along them as if through conduits. If such fields were to connect the galaxies within the void, then gas ejected from one galaxy could theoretically travel these lines of force to another. Yet, magnetic fields must have a source. They are generated by the movement of electrical charges or the spin of massive objects. Without a generator of some kind, such fields simply cannot exist. The profound emptiness of the void offers no clear candidate for producing magnetic fields powerful enough to bridge millions of light-years. An alternative is that the fields could be primordial, ancient remnants from the earliest moments of the universe, when conditions for their formation were more favorable. Over eons, these cosmic fields would have been stretched and weakened by universal expansion. It is conceivable, however, that inside the void, with its distinct properties, these fields might have endured with greater strength than they did elsewhere. The network of filaments itself possesses a remarkable structure. These are not arbitrary links between neighboring galaxies. Instead, the filaments connect the galaxies in a very specific arrangement. Mapping all of these connections reveals an underlying geometry of triangles, hexagons, and three-dimensional polyhedra. This is the very same geometric lattice that had been inferred from the positions of the galaxies and from gravitational anomalies, now made directly visible by the matter that links these cosmic nodes. This kind of arrangement is not what one would expect from natural formation. Random processes simply do not give rise to geometric networks. Gravity does pull matter into clumps and filaments, but those formations are typically irregular and chaotic, molded by a multitude of competing forces. The network in the void, by contrast, is orderly, symmetrical, and almost crystalline in its organization. Scientists who study pattern formation and the growth of crystals can recognize this type of structure. It bears a resemblance to how atoms align themselves within a crystal or how soap bubbles cluster together. These are minimum energy configurations, where each component settles into a position that perfectly balances all opposing forces. But crystals form on atomic scales, and soap bubbles on the scale of millimeters. This network spans a staggering 100 million light-years. To scale up such pattern formation to these immense dimensions would require conditions never before observed in nature. It would demand high symmetry, extremely low entropy, and total isolation from any random disturbances. The void does offer some of these prerequisites. Its emptiness shields the galaxies from external influences, and its vastness allows patterns to develop without interference. Still, something must be responsible for driving this organization. Some force or intelligence had to guide 60 galaxies into precise geometric locations and then connect them with these filaments. More recent observations have shown that the filaments are carrying more than just gas. They are coursing with electrical currents, a flow of actual electricity on a cosmic scale. These currents have been measured in the billions of amps, representing enough power to sustain entire civilizations. This discovery raises a host of new questions. Where is this electricity originating? What is generating it? And what is it being used for? For electricity to flow, a difference in electrical potential, or voltage, must exist. Something at one end of a filament must have a different electrical charge than the other. The current then moves between them in an attempt to equalize this potential. In ordinary space, such voltage differences are fleeting. Charges would redistribute almost instantly, neutralizing any imbalance. The extreme vacuum of the void might allow these potential differences to last longer, but they should still eventually dissipate. That is, unless something is actively maintaining them, like a cosmic battery or generator providing a continuous stream of power. One hypothesis posits that the 60 galaxies are themselves the source of the currents. Galaxies rotate, and rotating, charged material can create magnetic fields through a process known as dynamo action. If the rotation of these galaxies were somehow synchronized, they could potentially produce coordinated magnetic fields that would link together to form the observed network. This scenario, however, would require the galaxies to rotate in very specific directions and at very specific speeds. The statistical likelihood of 60 independent galaxies all achieving the necessary rotations by sheer coincidence is astronomically small. It suggests that someone, or something, must have synchronized them with intent. Another hypothesis centers on the radio source, suggesting it is the powerhouse for the entire network. In this view, the 14-day broadcasts are not attempts at communication, but are instead transmissions of power. Energy could be flowing from a central generator out through the filament network to each of the galaxies. The whole structure might be an enormous power grid stretched across the void. If that is the case, what could the galaxies be powering? What process is happening inside them that requires a continuous supply of billions of amps? Perhaps they are manufacturing something, or running vast computations, or maintaining stasis fields. The energy budget involved is simply staggering. Whatever is occurring consumes an amount of power equivalent to millions of stars. Perhaps the most disquieting observation is that the filaments are steadily intensifying in brightness. Year after year, the synchrotron emission they produce increases. This indicates that more charged particles are flowing through the network, which means more electrical current and more power. The entire system appears to be ramping up, as if in preparation for something. If this rate of brightening continues, the filaments could become luminous enough to be seen by optical telescopes in as little as 30 years. What now appear as faint radio threads would then glow with visible light. The geometric network would become undeniable to anyone with a telescope, providing clear evidence of something artificial within the void. Or perhaps it is not artificial at all. An alternative and more profound idea suggests the network may be alive. It could be a cosmic organism that uses galaxies as its neurons and the filaments as its axons. In this model, thoughts would propagate as electrical signals across a brain the size of the void itself. This would be a mind so vast and slow that a single thought might take years to complete. The 14-day radio pulse could be its heartbeat, and the 78-day dimming cycle could be its respiration. The geometric structure might simply be its anatomy. We could be witnessing a living being so fundamentally different from ourselves that we fail to even recognize it as life. And if it is alive, it appears to be waking up. The increasing activity, the brightening filaments, and the accumulation of energy could all be signs of a consciousness stirring from an eon-long slumber. The question then becomes, what will happen when it is fully awake? The very origin of the universe is a point of contention between quantum mechanics and general relativity. Quantum mechanics implies that the Big Bang was not a singular event. Instead, it was just one quantum fluctuation among a countless number of others. Each of these fluctuations has the potential to create a new universe, bubbling up from the quantum foam like froth on the ocean. These bubble universes expand, each creating its own space-time. On occasion, these bubbles might collide. When they do, such a collision would leave behind telltale marks, such as disruptions in the cosmic microwave background or unusual structures in the distribution of matter. These would be regions where the normal laws of physics seem to break down, because two different sets of physical laws were forced to coexist. Under this theory, the Boötes Void could be a scar from such a collision, a region where our own universe made contact with another during the initial period of cosmic inflation. This impact would have created an underdense region that eventually expanded into the void we see today. Such a scenario could explain many of the anomalies, including why the void is so large and why it contains such an unusual geometry. The theory that our universe collided with another makes a number of specific predictions about how such an event would affect the cosmic microwave background. First, the impact should have established a clear direction in space, an axis defined by the approach of the two bubbles. Along this axis, the void itself ought to appear elongated, and the CMB cold spot should show a corresponding asymmetry. Observations seem to confirm both of these points. The void does indeed stretch along a particular orientation, and the cold spot in the background radiation is elongated in precisely the same manner. What makes this compelling is that the alignment is not just similar, it is nearly identical, a detail that stands as one of the strongest pieces of evidence for the collision hypothesis. A second prediction is that the collision would have left behind a boundary, a thin shell where the distinct physics of the two universes met and merged. This seam might still be observable today as an unusual concentration of galaxies or a strange distribution of matter. Surveys of the void's perimeter have revealed a feature that matches this description exactly. One edge of the void is marked by an exceptionally dense wall of galaxies, far denser than the typical filament walls found elsewhere in the cosmos. The galaxies within this wall also exhibit peculiar properties. Their ages appear inconsistent with standard models of galactic formation, suggesting they were born under conditions different from those of ordinary galaxies. This wall could be the literal boundary of the impact, the place where material from both universes piled up. Galaxies that formed from this commingled matter would naturally inherit traits from both parent realities, causing them to look strange when compared to their conventional counterparts. Third, the other universe may have left actual remnants behind inside our own objects or fields that still operate under its physical laws instead of ours. Such relics would appear anomalous to our instruments, seeming to violate our laws of physics because they are not bound by them. This interpretation is particularly appealing to cosmologists because it offers a single, elegant explanation for all of the void's mysteries. The enigmatic radio signals, the unexplained dimming events, the geometric lattice, all could be traced back to a single cause: a collision with another universe. The simplicity and economy of this explanation are beautiful, but the hypothesis is not without its challenges. To begin with, the very existence of bubble universes is theoretical. We have no direct proof that they are real. The concept is built upon interpretations of quantum mechanics and inflation theory that remain subjects of debate among many physicists, making it a risky foundation for any explanation. Furthermore, even if bubble universes do exist, collisions between them are expected to be exceedingly rare. The probability of our universe striking another with just enough force to create the observed void but not enough to completely destroy everything is incredibly small. We may be invoking a highly unlikely event to account for our observations. Another significant problem is the timing. The collision would have taken place during inflation, some 13.8 billion years ago. Any residual activity from such an ancient event should have faded by now. The energy should have dispersed, and any remnants should be cold and inert. Yet, the void seems to be a place of increasing activity, where signals grow stronger and geometric patterns develop over time. This suggests ongoing processes, not the cooling embers of a distant cataclysm. Unless, that is, the collision did more than leave a scar. What if it created a permanent connection, a lasting bridge between the two universes? If our reality and another still touch at the location of the void, then matter and energy could potentially flow between them. Information could be transferred. Entities from the other universe might even be able to cross over. The void, in this view, would be a cosmic border crossing, a place where two separate realities meet. Recent theoretical work has begun to explore what such a connection might look like. The physics at the boundary would be exotic, a hybrid region where the laws of neither universe fully apply. In this zone, bizarre phenomena could become possible. This concept could explain the void's unique properties. The missing dark matter might have crossed over into the other universe. The anomalous lensing could be the result of space-time behaving according to foreign physics. The radio signals could be attempts at communication across the boundary, and the geometric structure could be a bridge that exists partially in both realities. If this model proves correct, it means we are not alone. Another cosmos lies adjacent to ours, with different physics, different constants, and perhaps different forms of matter and energy. Through the void, we may be able to observe it, study it, and learn from it. Some researchers have taken this idea even further, proposing that intelligence exists in the other universe. Perhaps advanced beings on the other side have discovered the connection, just as we are beginning to, and the signals we detect are their attempts to communicate with us. It is an optimistic thought, but there is another, darker interpretation. The other universe could be hostile, using the connection to expand into our space. The geometric lattice might be infrastructure for an invasion, and the radio signals could be coordinating its forces. The increasing activity we observe might represent the steady progress of this incursion. Without more data, we have no way to know if we are witnessing first contact with beings from a parallel cosmos or watching the opening stages of an inter-universal war. Either way, the void is more than an astronomical curiosity. It could be the most important discovery in human history, proof that our universe is not all there is, that reality is larger and more layered than we ever imagined. Temperature is simply a measure of particle motion. More motion translates to a higher temperature, while less motion means a lower one. At absolute zero, which is negative 460 degrees Fahrenheit, particles cease moving altogether. Space is profoundly cold. The cosmic microwave background radiation, or CMB, permeates the entire universe, bathing it in a faint glow with a temperature of negative 454 degrees Fahrenheit, just a few degrees above absolute zero. This is the baseline temperature of the cosmos. Empty space cannot get much colder than this because the CMB constantly warms it. The Boötes Void, however, is colder. Measurements reveal that the interior of the void registers at -456 degrees Fahrenheit, a full 2 degrees colder than the cosmic microwave background should allow. According to the laws of thermodynamics, this should be impossible. The CMB surrounds the void, flooding it with radiation from every direction. Nothing can be colder than its environment without some form of active cooling. Active cooling requires work. It involves extracting energy from a region and dumping it somewhere else, much like a refrigerator pumps heat from its interior to the outside. But space is not a refrigerator. There is no known mechanism that could cool a cosmic void below the ambient temperature of the universe. And yet, the void is consistently colder across its entire immense volume. Every measurement has confirmed it. The temperature drop is real. Some physicists have proposed that dark energy may be the cause of this chilling effect. The expansion of space, driven by dark energy, is a fundamental process that has a natural cooling effect on the universe. As the fabric of space-time stretches, it also cools. The void, however, appears to expand more rapidly than ordinary space, leading to a fascinating question about its temperature. Recent observations suggest this accelerated expansion might be cooling the void to a temperature below that of the cosmic microwave background radiation. Yet, when one calculates the amount of cooling that cosmic expansion alone could provide, the result is underwhelming. The effect is simply not powerful enough to account for the observed temperature drop. Expansion can only cool space by a mere fraction of a degree at most, while the measured difference is significantly larger. Clearly, some other mechanism must be at play. An alternative hypothesis points to the void's apparent lack of dark matter, which normally plays a role in distributing heat. Although dark matter does not emit light, it does engage in gravitational interactions that can effectively transfer energy. In a region without a significant dark matter presence, this energy transfer could happen much more slowly. The void might therefore be colder simply because it takes a very long time for ambient heat to permeate it. While this explanation is more compelling from a mathematical standpoint, it still falls short of fully explaining why the temperature remains persistently below the cosmic background level. Even a slow transfer of energy should, over a vast timescale, lead to thermal equilibrium. Given that 13 billion years have passed, the void should have warmed up to match the temperature of its surroundings. What stands out is that the temperature distribution is not uniform across the void. The coldest spots are concentrated around the geometric nodes of the lattice, precisely where the 60 galaxies are located. The space around the galaxies is the coldest of all. The filaments that connect these galactic nodes exhibit an intermediate level of cooling. In contrast, the vast, open regions between the elements of this lattice are only marginally cooler than normal space. This distinct pattern suggests that the lattice structure itself is actively drawing energy out of the surrounding space. It behaves like a cosmic refrigeration system, with the galaxies functioning as the cooling elements and the filaments acting as heat exchangers. Energy seems to flow from the emptiness of the void into the lattice, where it then disappears. This raises a critical question about where all that energy is going. The laws of thermodynamics insist on the conservation of energy. It cannot be created or destroyed, only moved or converted into another form. This implies the lattice must either be storing the energy or radiating it away somewhere else. However, extensive surveys conducted across all wavelengths have detected no excess radiation emanating from the lattice. The galaxies themselves glow with a normal intensity for their respective types. The filaments emit only the expected synchrotron radiation. There is no sign of any additional energy output that could possibly account for the cooling of such an immense volume of space. The only remaining possibility is that the energy is being stored, accumulating inside the lattice over billions of years. This is a deeply unsettling thought. Stored energy can, of course, be released. If 13 billion years worth of extracted thermal energy is currently contained within this structure, the total amount would be staggering. A sudden release of this magnitude would unleash more energy than billions of supernova explosions combined. The consequences of such an event are difficult to contemplate. It could potentially reignite dormant galaxies, tear apart neighboring cosmic structures, and generate powerful shockwaves that would propagate across the void. The resulting destruction would be visible even from our distant vantage point. Alternatively, the accumulated energy may not be for destruction. It could instead be fuel, collected to power whatever the lattice is designed to build. This geometric structure might be a machine of unimaginable scale, one that requires a tremendous amount of energy to operate. It has been gathering this fuel for eons and may now be nearly ready to activate. More recent temperature measurements have revealed something even more disturbing. The cooling process is accelerating. The void is now growing colder at a faster rate than it was just a decade ago. This implies the lattice's energy extraction rate is increasing, as if it is preparing for an operation that demands more power than ever before. If one extrapolates this trend into the future, the void is on a trajectory to reach absolute zero within a remarkably short cosmic span of 10,000 years. In our universe, nothing is known to exist at absolute zero. The principles of quantum mechanics actually forbid it. Reaching a true zero temperature would require the complete cessation of all particle motion, the elimination of all quantum fluctuations, and the removal of all zero-point energy. This is considered physically impossible within the framework of our space-time. And yet, the void is heading directly toward this state, cooling past the very point where our understanding of physics dictates that cooling must cease. This suggests the lattice can either access physical principles beyond our current comprehension, or that it is connected to something outside of our universe where different rules may apply. If the void does manage to reach absolute zero, what would happen? Would quantum effects simply shut down? Could space-time itself freeze solid? It raises the possibility that the void could become a region where causality breaks down and the flow of time halts, a bubble of absolute stillness within a dynamic cosmos. Or perhaps reaching absolute zero is not the final goal. It might be a necessary threshold, a specific condition that must be met before another process can begin. Much like a computer waiting for its processor to cool before executing a critical task, the lattice may be cooling the void to absolute zero before it activates and commences its true purpose. We have no way of knowing what that purpose might be. We only know that it seems to require conditions that violate our fundamental understanding of physics, and that those conditions are approaching with startling speed. The void grows colder with each passing day. When it finally reaches zero, we may discover what this structure has been preparing for all this time. Gravity is the primary force that drives the clustering of matter. Dense regions pull in nearby material, and over cosmic timescales, galaxies assemble into groups, which then merge into clusters, and finally form vast superclusters. This hierarchical pattern of structure formation is universal. Everywhere we look in the cosmos, we see it unfolding naturally. The 60 galaxies within the void, however, do not cluster correctly. They form groups that defy gravitational predictions. Some of these groups contain galaxies moving far too quickly to remain gravitationally bound to one another. They should have flown apart millions of years ago, yet they remain clustered, resisting the forces that are trying to separate them. Other groups contain galaxies that are moving too slowly. Their orbital speeds suggest they feel almost no gravitational attraction to each other, as if they are separated by invisible walls that prevent normal gravitational interaction. These galaxies stay in formation not because gravity is holding them together, but because something else is preventing them from leaving. Astronomers map the velocities of galaxies by analyzing Doppler shifts in their light. When a galaxy is moving toward us, its light is shifted to shorter, bluer wavelengths. When it moves away, its light shifts to longer, redder wavelengths. By measuring these shifts for many galaxies in a group, scientists can reconstruct their motions in 3 dimensions. The movements of the void galaxies reveal highly coordinated patterns. These are not the random orbits one would expect, but rather synchronized movements, like performers following intricate choreography. For instance, 6 galaxies near the void's northern edge are moving in precise circular paths around an empty point in space. They complete a single orbit every 90 million years, all while maintaining perfect spacing between one another. There is nothing at the center of these orbits, no massive object, no visible matter of any kind. These galaxies are circling a region of complete emptiness. When one calculates the mass required to keep 6 galaxies in such orbits at those speeds, the number is immense, equivalent to more than 100 billion stars. Yet observations show absolutely nothing there. This is not the typical behavior of dark matter, which clumps under gravity and concentrates where ordinary matter is found. In our understanding of the cosmos, the discovery of a vast dark matter halo entirely empty of normal matter would fundamentally contradict every accepted model of structure formation. The established theory is that ordinary matter and dark matter are bound together, growing in concert through their mutual gravitational attraction. It should not be possible to have one without the other. An alternative, though speculative, is that some unknown mechanism intervened after the dark matter halo took shape, somehow extracting all the ordinary matter. This would leave behind only a gravitational skeleton, an invisible framework that once anchored a galaxy. The galaxies we see in the void would therefore be orbiting these ghost structures, dark matter scaffolds that now stand vacant. The question this raises is profound. What kind of process could so selectively remove normal matter while leaving the dark matter completely undisturbed? We know of no physical force capable of such a thing. Given that normal matter and dark matter interact solely through gravity, any influence powerful enough to affect one should inevitably affect the other. The puzzle deepens when we consider another anomaly related to how the galaxies are clustered. Their distribution is not at all random. They actively steer clear of particular regions. There are specific volumes within the void that remain perfectly empty, even as galaxies travel close by. These zones of exclusion maintain their emptiness without any visible demarcation or boundary. Galaxies that venture too close to these areas are deflected, as if they have encountered some kind of invisible barrier. When these forbidden zones are mapped out, a startling pattern comes into view. They appear as spheres, arranged at regular intervals throughout the void. Intriguingly, the volumes where these spheres intersect are also forbidden to matter. The complete structure bears a striking resemblance to a 3-dimensional molecular lattice where the forbidden zones take the place of atoms and the available pathways between them act as the bonds. The 60 known galaxies in the void are found occupying the spaces between these spheres, residing only in the slots where matter is permitted to exist. When one calculates the total number of available slots this lattice provides, the number comes out to exactly 60, not 59, and not 61. It is a precise match for the number of galaxies observed, a fact that seems to defy mere coincidence. It is highly unlikely that the galaxies simply settled into a pre-existing lattice by chance. This suggests a more direct relationship. Either the galaxies themselves created this lattice, or the lattice dictated where the galaxies could form. Both of these scenarios would necessitate physics that is currently beyond our comprehension. Creating such forbidden zones would require something like force fields or powerful energy barriers, concepts that belong more to science fiction than to observed cosmic phenomena. And yet, the zones are real. Their effects on the motion of galaxies are demonstrably measurable, even if we cannot see the zones directly. Some theoretical physicists have proposed that the zones could be topological defects, which are hypothetical remnants from phase transitions in the early universe. These defects would be permanent features woven into the fabric of space-time. The problem with this idea is that topological defects have never been confirmed to exist. Using an unproven concept to explain a mysterious observation is a form of circular reasoning, where one unknown is used to justify another. The only other alternative is to consider that the lattice was constructed deliberately. This would imply that some intelligence placed 60 galaxies in these exact positions and actively maintains the forbidden zones between them. An entity operating on scales of time and space that are almost incomprehensible. What's more, these clustering patterns are not static, they appear to be evolving. Recent measurements show that the galaxies are slowly drifting into ever more perfect alignment with their lattice positions. The small deviations from geometric ideality are decreasing year by year. It seems the structure is in the process of refining itself, approaching a final, perfected configuration. This leads to a profound question. What happens when that configuration is complete? Does some cosmic machine then turn on? Does the lattice finally achieve its designed function? We may be watching a vast engineering project self-assemble across cosmic distances. A project that began before complex life ever appeared on Earth and is now nearing its completion. This entire phenomenon challenges a fundamental tenet of modern astronomy known as the cosmological principle. This principle asserts that the universe, when viewed on the largest scales, is homogeneous and isotropic, meaning it looks the same from every vantage point and in every direction. There are no special or preferred locations. This assumption is what makes the science of cosmology possible, as it allows us to extrapolate from our local observations to understand the universe as a whole. Without it, we could not be certain that the laws of physics are consistent across the cosmos. The Boötes Void, however, directly threatens this principle. It is not statistically similar to other regions of space. It is exceptional, a place where the normal rules appear to break down and something else is at play. If we compare this void to other large voids, they exhibit all the expected properties. They have the anticipated number of galaxies, normal effects on the cosmic microwave background, and standard rates of expansion. They are empty, but in an unremarkable way. The Boötes Void, by contrast, displays none of these typical traits. Every single measurable quantity deviates from our expectations. The galaxy count is far too low. The CMB cold spot is too cold. The local expansion is too fast, and the temperature is too low. On top of this, it contains geometric structures, broadcasts unexplained signals, and seems to channel energy along filaments. This is not a simple statistical fluctuation. While statistical outliers do occur, they usually deviate from the mean in only one or two properties. The void deviates in every single one. The mathematical odds of this happening randomly are infinitesimally small, effectively zero. We are therefore left with a choice between two extraordinary conclusions. Either we are witnessing a coincidence so rare it borders on impossible, or the cosmological principle is wrong. If it is wrong, it means that there is at least one region of space that is genuinely different from all others. It would be a place where physics itself operates differently, meaning the universe is not homogeneous at the largest scales. Should this be the case, our entire understanding of cosmology would need to be rebuilt from the ground up. Our models of cosmic evolution depend on the assumption of uniformity. They work by applying the same set of rules everywhere through time. Without uniformity, these models fail. We would need new theories that can account for special regions of space, zones where cosmic evolution may have followed an entirely different path. This would require us to identify what makes these zones distinct from normal space. The location of the void itself offers few clues. It sits in a relatively unremarkable area of the sky, not aligned with any major cosmic structure. There is no obvious reason why this particular spot should be special, unless its location was chosen. Such a possibility implies agency, intelligence, and purpose concepts that are entirely outside the scope of cosmological models. As a final attempt at a natural explanation, Some cosmologists have proposed that we could be observing a local bubble of false vacuum. According to this idea, in the early universe, space could have settled into various energy states. While most of the cosmos relaxed into the true vacuum, the lowest possible energy state, an occasional region might have become trapped in a higher energy state, a false vacuum, unable to decay because of surrounding energy barriers. Within a region of false vacuum, the fundamental characteristics of reality itself would be altered, giving rise to a space with distinct properties from the true vacuum we inhabit. The very nature of particle physics could be different. The strengths of the fundamental forces might be changed, and perhaps even the number of spatial dimensions would not be the same. The existence of such bubbles would naturally create violations of the cosmological principle, which posits a uniform universe, and this would require no intelligent intervention to occur. While the theory possesses a certain elegance, it also confronts significant challenges. Bubbles of false vacuum, with their higher energy state, should theoretically expand, not contract. This immense energy would drive them to grow relentlessly, converting the surrounding true vacuum into more false vacuum. In time, such a bubble would engulf the entire universe in a scenario known as vacuum decay, representing a potential end of everything event. And yet, the void in Eridanus does not behave this way. It is not expanding at a speed that would threaten the wider cosmos. While it does appear to be growing, its expansion is slow, making it the most stable bubble of its kind imaginable. Something is preventing it from either decaying or expanding catastrophically. An intriguing possibility is that the geometric lattice itself provides this stability. The structure could be regulating the process of vacuum decay, keeping the bubble from growing too quickly or collapsing entirely. This would be an engineered solution to what is normally a runaway natural process. This particular interpretation skillfully blends both natural and artificial explanations. It suggests the void began as a naturally occurring phenomenon, a false vacuum bubble that formed randomly in the early cosmos. But then, something discovered it, recognized its unique potential, and constructed the lattice to stabilize and control it, thereby transforming a natural curiosity into a powerful tool. This raises a compelling question. For what purpose would one harness a controlled false vacuum bubble? Inside such a bubble, the laws of physics are different from those on the outside. This would allow an occupant to work with different physical laws, to access far higher energy states, and to perform processes that are simply impossible in normal space. The bubble, in effect, becomes a vast physics laboratory, or an industrial facility operating under a customized set of rules. From this perspective, the radio signals we detect might be readouts from ongoing experiments, and the periodic dimming events could be byproducts of complex manufacturing processes. The energy observed flowing through the filaments might be powering exotic physics that require conditions we cannot naturally create. This line of reasoning suggests the void is not a threat to us. Instead, it is a piece of infrastructure, built by beings so advanced they can manipulate the fundamental fabric of physics. They may have chosen this specific location precisely because it already possessed unusual properties, which they then enhanced to create a facility that now spans an incredible 100 million light-years. But if they did build it, where are they now? Why does this monumental facility seem to be abandoned? Why do we detect these faint signals but no obvious operators? There are a few possibilities. Either its builders are long gone, or they are so fundamentally different from us that we are incapable of recognizing them, even when looking directly at their works. Or perhaps they are not gone at all. It is conceivable they are watching, waiting to see if we can figure out what it is we are looking at. They could be testing whether humanity is capable of recognizing artificial structures on cosmic scales, and in doing so, deciding if we are finally ready for contact. The cosmological principle has always seemed, to some, almost too good to be true, the idea that nothing in the universe is truly special and that we occupy no privileged position within it. Philosophically, it is a comforting notion. Reality, however, is not concerned with our comfort. The void seems to prove that some places are indeed special, and if one such place exists, others might as well. We could eventually find more structures like this one, more engineered cosmic facilities scattered across the heavens. An entire infrastructure spanning the observable universe might be hiding in plain sight, a network we have long mistaken for simple natural formations. Everything we thought we understood about the cosmos could be wrong, and we may be just now beginning to glimpse the truth. Our universe is defined by three spatial dimensions: left and right, forward and backward, up and down. Combined with the dimension of time, this creates the four-dimensional space-time we inhabit. Everything we see and experience exists within these dimensions. Modern physics, however, suggests that more dimensions may exist. String theory, for instance, requires a total of 10 dimensions to work, while M theory needs 11. These extra dimensions are thought to be hidden from us, perhaps curled up so small that we cannot detect them. Or maybe they are oriented in ways our three-dimensional senses simply cannot perceive. What if the void in Eridanus provides a connection to these extra dimensions? What if the signals we are detecting are merely echoes from a higher dimensional space? And what if the geometric lattice is just a projection, a shadow of a structure that exists primarily in dimensions we cannot see? While the notion may seem extraordinary, it offers an explanation for observations that otherwise remain elusive. Consider the puzzle of the missing dark matter. It is possible the dark matter is not missing at all. It might have simply shifted into an extra dimension, a place where we cannot detect its gravitational influence. The void could be a region where the barriers between dimensions are unusually weak, a place where matter can slip between these different levels of reality more easily than elsewhere. The impossible precision of the geometric lattice also begins to make sense if it is viewed as a shadow of a higher dimensional structure. In higher dimensions, creating perfect geometric patterns could be far easier than in our own. This is analogous to how a three-dimensional sphere can cast a perfectly circular two-dimensional shadow on a flat surface. The lattice we observe might be the three-dimensional shadow of a four-dimensional or even five-dimensional object. This would explain why the structure appears to defy our known laws of physics, because it is not fully contained within our space. Most of it could exist elsewhere, and we are only able to see the part that intersects with our dimensions. It is like watching someone's hand pass through a sheet of paper. The hand is a three-dimensional object, but any inhabitants of the paper would only perceive a changing two-dimensional cross-section. The radio signals could be a form of dimensional leakage, where energy propagating through higher dimensions occasionally crosses over into ours. We would then detect these crossing events as broadcasts. The 14-day periodicity could be a reflection of the geometry of that higher dimensional space, with the signal's complex path through these extra dimensions creating a delay that manifests as regular timing in our own. So far, experiments in particle physics have searched for signs of extra dimensions and have found none. But those experiments probe incredibly tiny, subatomic distances. It is possible for extra dimensions to be very large on cosmic scales, while remaining completely hidden at particle scales. The void could be situated at a unique location where these cosmic-scale extra dimensions become accessible. If we calculate what a four-dimensional sphere would look like as it passed through our three-dimensional space, a clear picture emerges. It would first appear as a single point, then grow into a sphere that expands to a maximum size, and finally, it would contract back down to a point before vanishing completely. The entire sequence would look like an object that appeared from nowhere, changed its size, and then disappeared. This pattern is a striking match for the observed dimming events. The galaxies seem to dim when this four-dimensional object passes through our particular slice of space, temporarily blocking their light. The magnitude of the dimming varies over time because different parts of the four-dimensional object have different cross-sectional sizes. The 78-day cycle, then, would simply represent the total amount of time the object takes to pass completely through our dimensional slice of reality. One interpretation of this cosmic mystery involves either 17 distinct four-dimensional objects or a single, vast, four-dimensional structure composed of 17 parts, each intersecting our own space at separate intervals. In either scenario, what we are observing is something that exists primarily beyond the range of our normal perception. The notable drop in temperature also aligns with this dimensional hypothesis. It is conceivable that heat within our three dimensions could be flowing into these additional dimensions, where it becomes impossible for us to measure. The void, therefore, is not colder because energy has been annihilated. It is colder because that energy has escaped into dimensions our instruments cannot reach. The lattice itself might function as a kind of dimensional heat pump, facilitating the transfer of this energy. The concept of higher dimensions also offers a natural framework for understanding effects that appear to exceed the speed of light. If signals were able to take a shortcut through these extra dimensions, they would seem to travel faster than light from our three-dimensional perspective. This is often compared to an ant walking on a rolled-up sheet of paper. The ant perceives a long journey across the two-dimensional surface, but if it could burrow through the paper's minimal thickness, the trip would be substantially shorter. The void could represent a cosmic shortcut of this kind, a region where these extra-dimensional pathways become accessible. In this model, signals and even matter could enter the void, pass through higher dimensions, and then re-emerge at another location in our universe almost instantly. The geometric lattice might be the very structure that serves as an entrance, a gateway between dimensions. If this were true, the implications would be staggering. Faster than light travel could be achievable by utilizing these higher dimensional shortcuts. The void would then be transformed from a mere astronomical curiosity into a potential hub for transportation, a natural network of wormholes integrated into the very fabric of space-time. There is, however, a more unsettling possibility to consider. What might inhabit these extra dimensions? If dimensions beyond our own perception are real, they could be home to entities that we are incapable of detecting. These could be beings that exist primarily in a four-dimensional or five-dimensional space. From their vantage point, our entire three-dimensional universe might appear as a simple surface that they can observe from above. Such beings would be able to see everything in our universe at the same time, all of space laid out at once. They could potentially reach into our dimensions at will, manipulating matter and energy with forces we cannot perceive. From our limited perspective, they would be effectively omnipotent. The lattice, in this context, might be their creation, a piece of infrastructure built by higher dimensional entities for purposes we can scarcely begin to comprehend. We would be attempting to understand a four-dimensional machine using only three-dimensional observations, much like a figure in a painting trying to understand the artist who created it. Recent theoretical work has begun to explore the kinds of signatures that higher dimensional objects would leave behind. These theories predict specific patterns in gravitational waves and unusual correlations between distant areas of space. They also predict apparent violations of energy conservation that are resolved only when the extra dimensions are factored into the calculations. Intriguingly, the void displays all of these predicted signatures. Gravitational wave detectors have registered a persistent hum originating from that direction. Galaxies on opposite sides of the void exhibit coordinated behaviors that defy conventional explanation. Energy seems to appear and disappear without any clear source or destination. Every anomaly appears to point toward the influence of dimensional physics. If we are indeed detecting another dimension, the consequences are profound. It would mean our universe is not an isolated system, but is connected to a much larger reality. Other dimensions exist, and they interact with our own. The void is simply the place where that interaction is most pronounced. And something within those other dimensions seems to be very interested in our region of space. It appears they have constructed vast structures spanning hundreds of millions of light years, and they seem to be actively maintaining them. They may even be broadcasting signals into our dimensions, perhaps attempting to establish contact or preparing for an unknown event. We are unable to see them directly, yet they can likely see us, and it seems they are preparing to act. In astronomy, computer simulations serve as a kind of crystal ball. Since we cannot wait billions of years to watch cosmic evolution unfold, we program the laws of physics into computers and allow them to calculate what should occur over time. These simulations are incredibly sophisticated, modeling gravity, dark matter, dark energy, gas dynamics, and star formation, tracking billions of particles as they interact across cosmic history. The results of these simulations match observational data with beautiful precision. The distribution of galaxies, the typical sizes of voids, and the masses of clusters all align with what we see. The single exception is the Boötes Void. The simulations are simply unable to reproduce it. Regardless of the initial conditions researchers input, and no matter which parameters they adjust, they cannot generate a void of this nature. After running 1,000 simulations, not one has produced a void that is 330 million light-years across. The largest voids that form in these models max out at around 200 million light-years. While increasing the strength of dark energy does cause voids to grow larger, it comes at the cost of breaking other structures, making the simulated universe unstable as galaxies fly apart. The model then fails to match observations everywhere else. In response, researchers have tried different approaches. Perhaps the void began with unusual initial conditions, originating from a region that had far less matter than the cosmic average. When this scenario is programmed into the simulations, an underdense region does indeed grow into a void, but its evolution is incorrect. It either forms too early or too late, never appearing at the right time with the right characteristics. The timing simply does not work, no matter how the parameters are tuned. Another approach involves testing whether something happened after the Big Bang, some specific event that carved out the void. Researchers have simulated explosive events, massive ejections of matter, and powerful bursts of energy. Yet nothing creates the observed structure without also destroying the galaxies nearby. The geometric lattice presents an even more significant problem for these models. Naturalistic simulations never produce such geometric patterns. Gravity creates clumps and filaments, but these formations are always irregular. Random processes are incapable of generating the kind of precise symmetry we observe in the void. Some researchers have tried inserting artificial structures into their simulations. They might place 60 galaxies in a geometric lattice, add connecting filaments, and then let the system evolve according to the laws of physics. The result is always the same. The lattice collapses almost immediately. The galaxies fall toward one another, and within a few million simulated years, they merge into disorganized clumps. The geometric pattern completely disintegrates. There are no known natural forces that can maintain such a structure against the relentless pull of gravity. Even when adding concentrations of dark matter at the lattice nodes or strengthening magnetic fields along the filaments, the structure still collapses. These measures can slow the collapse, but they cannot stop it. In the end, gravity always wins, and the pattern vanishes. Only one configuration has ever remained stable in these simulations. This occurs when researchers add invisible masses, precisely calculated to balance every single force acting on the lattice. However, these masses must be positioned with exquisite precision. If any single mass is shifted by as little as 1%, the entire lattice destabilizes. This level of precision requires an extraordinary degree of fine-tuning. Everything must be exactly right, or the entire structure fails to work. The processes of nature tend to be approximate and inexact, rather than finely tuned. It is intelligence that engages in fine-tuning, a capacity rooted in the ability to calculate specific values and then implement them with precision. Computer models also struggle to replicate the rate at which the void is expanding. When scientists input the observed positions and velocities of galaxies into a simulation and run it backward through time, the results are problematic. The goal is to see where these galaxies were billions of years in the past, but their calculated trajectories simply do not function correctly when traced back to the Big Bang. Instead of converging on plausible points of origin, the galaxies follow paths that are inconsistent with a shared beginning. Some of the galaxies appear to originate from directions where no matter was present in the early universe. Others are projected onto courses that would have required them to pass directly through one another. The resulting history fails to align with physical reality. The effect is similar to watching a film in reverse and witnessing events that defy logic, such as objects materializing from nothing or following paths that contradict the fundamental laws of conservation. This suggests that the void's present condition could not have emerged from any believable past state through the known mechanisms of natural evolution. Some researchers have put forward the idea that the physics programmed into these simulations is simply incomplete, arguing that we must be overlooking some crucial cosmic processes. Perhaps the behavior of dark energy is different from our models, or maybe dark matter possesses additional interactions we have yet to discover. The hope is that adding the correct missing physics might allow the simulations to finally reproduce the void. The question, however, is what this missing physics could be. Every adjustment that researchers have attempted either provides no benefit or compromises other established predictions. If a change fixes the void, it might disrupt models of galaxy formation elsewhere in the universe, or it could create a conflict with observations of the CMBB, or contradict data from gravitational wave detections. The observations we have of the cosmos form a deeply interconnected web of evidence. When one strand is touched, the entire structure shifts. The most unsettling results, however, come from simulations that evolve forward in time. When scientists take the void's current state as a starting point and run models into the future, a strange thing happens. The simulations literally crash within a few 100 million simulated years. The underlying mathematical equations reach a point where they can no longer be solved. Infinities begin to appear, causing physical quantities to diverge toward impossible values. The computer is unable to calculate the next step because the mathematics itself breaks down. This kind of failure is unprecedented in cosmic simulations. It is normally possible to simulate the entire lifespan of the universe, from the Big Bang to its eventual heat death, without encountering such problems. Yet, when modeling the void's future, researchers hit a wall, a point where the known laws of physics cease to function. Mathematicians are familiar with this signature. It is a phenomenon that occurs when attempting to model singularities, which are points where the curvature of space-time becomes infinite. Similar to the centers of black holes, the equations fail because the physical situation extends beyond the limits of classical physics. This raises an extraordinary question. Is the void in the process of creating a singularity? Is it evolving toward a point where the fabric of space-time itself will break? The simulations indicate this could occur in 500 million years, and perhaps even sooner. The growing activity of the lattice might be accelerating this timeline. When physicists model the formation of a black hole, the cause of the singularity is well understood. Matter is compressed to an infinite density, and gravity overpowers all other forces. The outcome is predictable, even if the mathematics at the very center falters. The approaching singularity within the void, however, has no apparent cause. Nothing is being compressed, and there is no evidence of runaway gravity. The region is, by definition, empty. Despite this, the simulations show the curvature of space-time increasing without any limit. It is as if the void is generating a naked singularity, a rupture in the laws of physics occurring in the absence of any matter. Such naked singularities are thought to be forbidden by the cosmic censorship hypothesis. They are not supposed to exist because their presence would permit violations of causality, leading to time travel paradoxes where signals from the future could influence the past. Physics itself would become inconsistent. Nevertheless, the simulations show one forming. In the most vacant region of the observable universe, at a location marked by an artificial geometric structure, the void is more than just an anomaly. It appears to be building toward an event that should be physically impossible. And when that event takes place, our simulations offer no insight into what happens next. We are effectively blind to the future beyond that point. The void is creating its own horizon, a boundary that limits our ability to predict, a frontier beyond which science cannot see. Our time to comprehend this phenomenon is diminishing. The singularity approaches, the lattice activates, and we remain unaware of its ultimate purpose. We know that mass and energy warp space-time. By measuring this warping, we can calculate the amount of mass responsible for it. This is a technique that allows us to weigh cosmic structures even when they cannot be seen directly. It is how dark matter is revealed, how the masses of galaxy clusters are mapped, and how we understand the mass distribution of the universe. When this same technique is applied to the void, the result is astonishing. The region's mass is incorrect, and not by a small margin, but by a catastrophic one. The mass deficit is equivalent to 10,000 galaxy clusters. The matter that ought to be there is simply gone. Each of these galaxy clusters contains a mass hundreds of trillions of times greater than that of our own planet. Multiplying that figure by 10,000 yields a mass deficit that surpasses the visible matter contained in millions of galaxies. This is no longer a question of missing dark matter. It is a case of missing everything. The immediate question is where it all went. Matter does not simply vanish. The conservation of energy is one of the most fundamental laws of physics. Mass energy cannot be destroyed. It can only be converted into other forms or relocated. The mass energy equivalent of 10,000 galaxy clusters has gone somewhere. When scientists calculate when this mass disappeared, they find no answer. The void has been undermassive since our earliest measurements. Historical data confirms the deficit existed decades ago, and extrapolating further back suggests it was present billions of years ago. Either the matter never arrived in that region to begin with, or it vanished so long ago that we can no longer determine when it happened. Some cosmologists have proposed that primordial conditions are responsible. Perhaps this region of space always had less mass than the average. The Big Bang may have distributed matter unevenly, and by sheer chance, this particular spot received far less than it should have. This underdensity would have persisted and grown into the void we see today. However, when the probability of such an extreme underdensity forming naturally is calculated, the result is a number with dozens of zeros after the decimal point. It is, for all practical purposes, impossible. Statistical fluctuations do not create outliers of this magnitude, not in a universe of our finite size and age. An alternative theory points to a cosmic catastrophe. It is possible that a galaxy supercluster formed in this region billions of years ago and was subsequently destroyed. This could have been a collision with antimatter, or a vacuum decay bubble, or some other unknown disaster that annihilated mass on a scale never before imagined. Yet, the annihilation of antimatter would produce a flood of gamma rays, and we should be able to detect the residual radiation from such an event. Space tends to remember catastrophes. The energy released cannot just disappear. It would thermalize and remain detectable. We observe no such residue. A vacuum decay event would leave different signatures, as a bubble of true vacuum expanding at the speed of light would create visible boundaries. A phase transition from a false vacuum to a true one should produce an intensely luminous boundary wall, yet no such brilliant border is observed around the void. Its edges appear entirely normal. This absence leads to a third, more disquieting explanation: theft. The idea is that something intentionally took the mass, deliberately extracting it from our universe to either transport it elsewhere or convert it into a usable form of energy. The matter from 10,000 galaxy clusters would represent a power source beyond our comprehension. One can only speculate what could be accomplished with that much energy powering entire civilizations, artificially illuminating galaxies, manufacturing planets, or even stabilizing wormholes and manipulating space-time on cosmic scales. It is conceivable the missing mass was fuel consumed by a process so profoundly advanced that we cannot even recognize it as technology. The geometric lattice we observe could be what remains, an infrastructure constructed with a mere fraction of the harvested material, while the rest was transformed into energy and expended. In this view, the lattice is the finished product, a structure that required the substance of 10,000 galaxy clusters to build. This represents a terrifying degree of engineering. Humanity struggles with the challenge of moving a single asteroid, whereas this hypothetical civilization would be relocating entire clusters of galaxies. The disparity in scale is almost unimaginable, akin to comparing an ant to a galaxy. We simply lack the conceptual framework to grasp engineering at this level. Recent surveys have searched for any signature left behind by the missing mass. If it was converted into energy, the second law of thermodynamics guarantees that even a perfectly efficient conversion would produce some amount of waste heat. Because absolute efficiency is impossible, a portion of the energy must inevitably leak out as thermal radiation. By calculating the maximum possible efficiency, scientists could then determine the minimum waste heat that should be detectable. Searches for this excess heat surrounding the void have found nothing. There is no temperature excess, no unexpected infrared radiation. This outcome suggests one of two possibilities. Either the conversion efficiency somehow exceeded known theoretical limits, or the waste heat was radiated into dimensions we are unable to observe. This latter option connects to theories involving higher dimensions. If the lattice does indeed connect to extra dimensions, waste heat could be dumped there, rendering it completely invisible to our instruments. From our limited perspective, the process would appear impossibly efficient. When the distribution of the mass deficit is mapped, it follows the geometric lattice with remarkable precision. The deepest deficits are located at the nodes of the structure, while the filaments exhibit more moderate deficits. The empty regions between the elements of the lattice show only a minimal lack of mass, as if the material was selectively removed from specific locations, harvested according to a detailed plan. This selective extraction seems to preclude natural processes. Nature does not preferentially remove matter in geometric patterns. Gravity clumps matter together more or less uniformly. Only intelligence removes material with such selectivity, and only engineering could create such a structured void. More unsettling still, the deficit is growing. Year by year, the void becomes slightly less massive. The rate is small, equivalent to only a few galaxy masses disappearing annually, but the process is consistent and ongoing. It is as if the extraction never stopped, as if something is still feeding on the matter within the void. This raises a critical question about what might happen when the deficit reaches a certain threshold. Is there a limit to how much mass can be removed before space-time itself destabilizes? Our simulations crash before they can answer this, but they crash for a reason. The mathematics points toward an impending instability. Perhaps the lattice itself is a mechanism to prevent such a collapse, a way to carefully remove mass while maintaining the integrity of space-time. This would be an extraordinary feat of engineering, walking a fine line between collecting resources and causing the region's destruction, all while keeping the cosmic structure stable. Or perhaps instability is the goal. The entire project could be aimed at deliberately destabilizing this region, to create a rupture in space-time, a breakdown that serves some purpose we cannot fathom. In this scenario, the missing mass is not waste, but a sacrifice, material removed to achieve a specific, catastrophic outcome. Either interpretation leads to the same conclusion. The void is an active engineering project. Something is reshaping the cosmic structure on the largest scales we can observe, using a technology so advanced it appears indistinguishable from fundamental physics. And we have only just noticed. After billions of years of construction, human instruments have finally become sensitive enough to detect the project. We are witnessing what may be the final stages of something that began before our planet even existed. The question is whether we can understand what we are seeing before it finishes, or whether its completion will surprise us as thoroughly as its discovery did. Astronomers observe the universe across many wavelengths, from radio waves and microwaves to infrared, visible light, ultraviolet, X-rays, and gamma rays. Each wavelength reveals different phenomena. Hot gas glows in X-rays, dust shines in infrared, and stars dominate the visible light spectrum. Most cosmic structures appear in some wavelengths but not others. For example, galaxy clusters blaze in X-rays from their hot gas but barely show up in radio waves. Dust clouds that hide visible light can glow brightly in the infrared. When you look at the same region in different wavelengths, you see completely different things. The Boötes Void, however, appears in all of them. Every telescope aimed at this region, regardless of the frequencies it observes, detects anomalies. This is unprecedented. No other structure shows such universal wavelength signatures. Starting with radio observations, the void is radio faint, with fewer sources emitting radio waves than in normal space, which is expected for an empty region. But the structure within that faintness is wrong. The geometric patterns and what seem to be periodic broadcasts should not exist. In microwaves, we see the cosmic microwave background cold spot, a temperature depression that violates thermodynamic expectations. It is visible across the entire microwave spectrum, not just one frequency, meaning the cooling is wavelength independent. Infrared observations show this temperature deficit extending to longer wavelengths. Dust that should be radiating heat is not, making the void darker in infrared than the surrounding space. Yet, this is also where those elevated edge temperatures are found, a simultaneous cooling and heating that makes no thermal sense. Visible light reveals the geometric lattice directly. The 60 galaxies arranged in an impossible configuration, their coordinated dimming, and the filaments connecting them. Everything visible to optical telescopes screams of artificial organization. Ultraviolet imaging of the stellar populations in the void's galaxies reveals they are wrong, too old and too red. Stars that should have died billions of years ago somehow persist, as if time flows differently for them. Finally, X-rays should show nothing, as the gas should have been evacuated. Instead, X-ray telescopes detect faint, structured emission lines connecting the lattice nodes, evidence of million-degree gas where no such gas should be. A substance can exist in a state of being both present and absent simultaneously, and this picture is further complicated by the detection of gamma rays. As the highest energy photons known, they typically originate from violent cosmic phenomena, such as the jets of black holes, the remnants of supernovae, or active galactic nuclei. The void, however, shows no evidence of such powerful sources. Despite this, gamma ray detectors register a diffuse emission that permeates the entire region. It is a low-intensity but constant background glow, with no discernible origin. While each wavelength of light, viewed in isolation, reveals anomalies, observing them together paints a picture of something fundamentally unusual about this area of space. The void is not merely empty, it is a region that behaves abnormally across the full range of energy scales. From the lowest radio frequencies to the most energetic gamma rays, every observation seems slightly askew. Certain wavelengths that ought to correlate with one another simply do not. For instance, hot gas is known to generate both X-rays and visible light from its excited atoms. yet the void's X-ray and visible emissions fail to align. They reveal different underlying structures, as if two separate phenomena were occupying the same volume of space without interacting. This particular quality is characteristic of objects from higher dimensions. An object existing primarily in extra dimensions would engage with our spacetime in varied ways at different energy levels. Lower energy photons would probe one of its facets, while higher energy photons would sample another. The observed dependence on wavelength would therefore reflect a dimensional structure rather than a physical composition. Researchers have compiled multi-wavelength maps, superimposing observations from radio, infrared, visible, and X-ray telescopes. The geometric lattice is apparent in all of them, though each map emphasizes different details. Radio waves appear to trace a network of communication, while infrared light reveals pathways of energy flow. Visible light maps the distribution of matter, and X-rays highlight high-energy processes. When all these wavelengths are combined, a complete image emerges, that of a machine. It is an enormous structure that operates across all energy scales at once. Each wavelength offers a glimpse of a single component, but the entirety of the structure becomes clear only when everything is viewed in concert. This multi-wavelength coherence provides a compelling signature of engineering. Natural phenomena present differently at various wavelengths because they are driven by distinct processes at different energies. Only systems that have been designed maintain such coherence across all observational bands. Only machines constructed for specific purposes would exhibit these kinds of coordinated, multi-wavelength signatures. We can now assert with a degree of confidence that the void is a machine. The data from the various wavelengths supports this conclusion. Whether it is biological or technological, natural or artificial, it is undeniably a structured system with components functioning across the entire energy spectrum. Recent observations have added neutrino detection to this catalogue of wavelengths. Neutrinos are particles that interact so weakly with matter they can pass through entire planets unimpeded. Detecting cosmic neutrinos is an exceptionally challenging task, requiring massive underground detectors filled with ultra-pure water. These instruments have found an excess of neutrinos originating from the direction of the void. The number is not large, just a few more than would be expected from background radiation, but the result is statistically significant. The void is producing neutrinos. Something within it generates these elusive particles and sends them streaming out into space. Neutrinos are typically the product of nuclear reactions, like fusion inside stars, radioactive decay, or particle collisions in high-energy environments. Since the void contains almost no stars and very little matter, the question of what nuclear processes could be creating its neutrinos is a profound one. Perhaps the lattice itself runs on fusion, with immense reactors powered by hydrogen gathered from the sparse gas in the void, converting mass into the energy needed to power the structure's functions. In this scenario, the neutrinos would be byproducts of fusion, an unavoidable waste from the conversion of matter to energy. Alternatively, the neutrinos could be intentional signals, particles chosen specifically for their ability to pass through anything, representing a form of communication that cannot be obstructed. These could be messages sent in pulses of neutrinos, traversing the universe without interference. In either case, the emission of neutrinos adds yet another layer to the multi-wavelength portrait. From the longest radio waves to the shortest gamma rays, and now to neutrinos that barely interact at all, the void communicates in every language of physics. It appears to be calling out across all possible channels, announcing its existence in every way that matter and energy can manifest. It is almost as if it wants to be found, as if it has been waiting for someone to develop instruments sophisticated enough to perceive it in its entirety. We have finally reached that point with our technology. We can now observe across the complete electromagnetic spectrum and also detect neutrinos and gravitational waves. We possess the ability to see the void for what it truly is, And what we are seeing is unmistakable. A machine built on a cosmic scale, operating for billions of years, using principles of physics we are only beginning to grasp to achieve goals we cannot yet comprehend. But now that we can see it, now that we recognize what we are looking at, the machine's behavior has begun to change. The signals are growing more intense. The structure is activating more fully, as if it were waiting for us to take notice. It is as if being observed was part of its purpose all along. This has led to a division among scientists into two main camps. One group believes the void represents genuinely exotic physics, a collision with a parallel universe, contact with a higher dimension, or an artificial megastructure, something real and without precedent. The other group suspects we are making measurement errors, misinterpreting the data, or simply seeing patterns in random noise. The skeptics raise valid points. Extraordinary claims must be supported by extraordinary evidence. The properties of the void are so unusual that systematic errors in measurement seem a more plausible explanation than revolutionary new physics. It is possible our instruments are miscalibrated. It is also possible that multiple small errors are compounding to create what appear to be impossibilities. We could be deceiving ourselves. Instrument error is a constant factor in astronomy. Telescopes can malfunction, detectors can drift, and calibrations can slip. Careful scientists check and recheck every piece of data. They exhaust all mundane explanations before they consider more exotic ones, as this is the proper scientific method. The void, however, has withstood every such check. Multiple independent teams, using different telescopes, have confirmed each of the anomalies. Radio observations from the Very Large Array, optical imaging from the Hubble Space Telescope and ground-based observatories, X-ray data from the Chandra X-ray Observatory, and infrared data from the Spitzer Space Telescope all tell the same consistent story. The void is abnormal. Statistical analysis indicates that the probability of coordinated measurement errors occurring across all of these independent systems is negligible. It would require every major telescope in the world to malfunction in precisely the same manner. The instruments would essentially need to conspire to generate consistent, fabricated signals, an idea that borders on the absurd. In response, the skeptics have shifted their arguments. Perhaps the anomalies are real, but their origin is natural. Maybe we have discovered a new aspect of physics that is not exotic, but simply unknown to us. It is conceivable that dark matter could behave in ways we do not expect, or that dark energy might possess additional properties we have not yet identified. The puzzles of the void resist solutions based on modified standard physics, not because revolutionary changes are needed, but because even minor adjustments create new problems. Every proposed tweak that accounts for one strange observation seems to invalidate another established principle. If dark matter is made to self-interact with enough force to explain the missing mass, for instance, our models of galaxy clusters fall apart. If dark energy is altered to drive the void's expansion, it contradicts precise predictions derived from the cosmic microwave background. The anomalies are not isolated issues. They are an interconnected system that pushes back against piecemeal theories. In this context, the hypothesis of a parallel universe offers a compelling alternative, as it could address all the discrepancies at once. If our own cosmos were to make contact with another at that specific location in space, it could potentially explain everything. The void's enormous size, its deficit of mass, the strange geometric arrangements, and its multi-wavelength signatures could all stem from a single cause. Physicists find this economy of explanation highly appealing, as it aligns with the principle of Occam's razor, which favors the simplest solution. A collision between universes is, in a way, a simpler concept than a whole series of unrelated and highly improbable events, all occurring in the same place by sheer coincidence. The great challenge, however, is that parallel universes remain unproven, existing as theoretical possibilities rather than confirmed realities. To build an entire explanation on such speculative physics is a significant risk. The entire hypothesis would collapse if parallel universes are found not to exist. Yet, recent developments have started to lend more weight to this kind of exotic explanation. The signals emanating from the void are becoming too distinct to simply ignore. The radio broadcasts, with their 14-day cycle, show no fluctuation or drift in their timing. For years, they have maintained this perfect rhythm. Natural astrophysical phenomena are almost never this consistent. The spin of pulsars can drift over time, and the periods of variable stars are known to change. Such unwavering precision is typically associated only with artificial sources or the most fundamental laws of physics. The geometric lattice of galaxies is an even more compelling piece of evidence. When independent teams of skeptical researchers measured the positions of the galaxies, their findings confirmed the geometric relationships. Using triangulation from different vantage points, they were able to rule out the possibility of a mere projection effect. The lattice is a real, three-dimensional structure. It is difficult to conceive of a natural process that could create a geometric crystal of this kind, spanning hundreds of millions of light-years. There comes a point where continued skepticism begins to look more like denial, when every new test confirms the exotic behavior, and when all mundane explanations have been exhausted, one must consider that something genuinely unusual is taking place. The void appears to have crossed that threshold. Now, even the most hardened skeptics are conceding that something unprecedented exists within it. The focus of the debate has shifted from whether the void is unusual to what, precisely, it represents. Contact with a parallel universe is still a leading possibility. However, other theories, such as the influence of higher dimensional physics, the formation of vacuum decay bubbles, or the presence of artificial megastructures, also seem to fit the observations. A number of exotic explanations are now in competition. What they all share is the consensus that the void is not a normal region of space. Some researchers have adopted a middle ground. Perhaps the void began as a natural anomaly that was later discovered and modified by something else. In this view, a naturally occurring flaw in spacetime was recognized and then exploited by an advanced civilization. The initial formation would have been a coincidence, but the structure we see today is the result of engineering built upon that foundation. While this compromise may not fully satisfy the skeptics or the proponents of exotic theories, it might be the closest to the truth. Nature could have provided the unusual starting conditions, and intelligence then took advantage of them to build something new. The void would therefore be a hybrid, part natural and part artificial, a blend of cosmic accident and deliberate construction. To distinguish between these competing exotic explanations, new kinds of observations are required. If it is contact with a parallel universe, we might expect to detect particles or forces that are unknown to our physics. If higher dimensions are involved, we might see correlations between distant regions of the void, suggesting the existence of shortcut connections through space. And if the structure is artificial, we should be able to find components arranged for maximum efficiency, a signature of optimization. A recent analysis has, in fact, found evidence of such an optimization signature. The geometric lattice is not just any random geometric pattern. It appears to be the optimal configuration for its size, given certain engineering constraints. Specifically, the arrangement minimizes the expenditure of energy while maximizing the connectivity between its nodes. This is what engineers would describe as an optimal solution. Natural processes, by contrast, do not optimize. They tend to settle into local minima, finding solutions that are good enough, but not necessarily perfect. Only intelligence engages in optimization, because only intelligence can evaluate a vast range of possibilities and select the very best one. The optimal geometry of the void is therefore strong evidence for an artificial origin. But this conclusion raises a host of uncomfortable questions. Who built it? For what purpose? And when? If this structure is artificial, It represents a level of engineering capability that far exceeds human comprehension. Its builders would be able to manipulate matter on cosmic scales and maintain their creations for billions of years. It is even possible that they are still watching over their work, and if they are watching, they would know that we have discovered it. Our observations are not passive. Every telescope we point at the void announces our presence. If the builders exist, they are now aware that intelligent life has emerged in their observable vicinity. They know we are studying their structure. What happens next would depend entirely on their intentions. Are we like ants that have stumbled upon a power station too insignificant to warrant their notice? Or are we interesting enough for them to make contact? Will they reach out to us and explain the purpose of the void? Or could they view us as a threat, a primitive species that might one day interfere with their project, and which is better eliminated now before it can develop further? We simply do not know. We can only continue to watch the void and hope that whatever controls it is either indifferent or benevolent. Because if it is hostile, we would have no defense against entities that can engineer on such a scale. The idea that this is all a measurement error looks more attractive with each passing day. But the data refuses to cooperate. The anomalies persist. The void is real, and we must be prepared to face whatever that reality implies. For decades, the Boötes Void was considered a solitary mystery, an isolated phenomenon. No other void exhibited comparable properties. Astronomers generally assumed it was unique, a one-in-a-universe curiosity. Then, just last year, surveys began to uncover similar structures, not identical, but with disturbing parallels. 3 other voids, located in distant regions of the sky, were found to have geometric lattice patterns. They are smaller than the one in Boötes and seem less developed, but their organization is unmistakably similar. The first of these discoveries came from the Sloan Digital Sky Survey. Automated algorithms designed to search for cosmic voids flagged an unusual structure about 90 degrees away from Boötes. This was the Eridanus supervoid, which is larger than a typical void but smaller than Boötes, measuring around 200 million light-years across. Deeper imaging revealed that it contains 40 galaxies, and they are arranged geometrically. The structure is not as perfect as the Boötes lattice, but it clearly shows structured triangular patterns and regular spacing, the signature of organization rather than randomness. The Eridanus void also exhibits radio emissions. They are at a different frequency from those in Boötes and have a 28-day periodicity instead of 14, but their character is unmistakably similar. What had seemed a singular anomaly was soon revealed to be something more. A source was broadcasting with scheduled precision from the depths of space, and just 2 months later, another structured void was identified by astronomical surveys. This was the Sculptor Void, located in the southern celestial hemisphere and spanning an immense 150 million light-years. Inside, observers found 23 galaxies organized into a geometric pattern, and from it emanated radio emissions that repeated every 41 days. The characteristics were strikingly similar to the Boötes Void, yet not an exact copy. More recently, a third example came into view, the Canes Venatici Void. It was the smallest of this emerging group, measuring 100 million light-years in diameter and containing only 15 galaxies, but their arrangement was perfectly ordered. Its radio signal had a periodicity of just 7 days, suggesting it might be the youngest or perhaps the least developed of these formations. With this discovery, a total of 4 such voids were now known, all sharing a remarkable set of properties. Each one contained galaxies positioned in geometric configurations. Each one broadcast periodic radio signals, and each one exhibited unusual temperature profiles and a significant deficit of mass. The pattern that emerged was undeniable, fundamentally altering our cosmic perspective. The Boötes Void was not a unique phenomenon. Rather, it was the largest and most mature member of an entire family of objects. This was a new category of cosmic structure, one whose existence had never before been suspected. These structured voids appear to be distributed throughout the observable universe. When the positions of the 4 known voids are mapped, a curious detail emerges. They do not cluster together in one area of the sky. Instead, they are spread out evenly, as if they were sampling different regions of the cosmos, or perhaps as if they were deliberately placed to achieve maximum coverage. An analysis of their distances reveals another layer to this pattern. They reside at varying depths from our vantage point. Boötes is the nearest, at a distance of 300 million light-years. The Eridanus void lies farther out, at 400 million light-years. The Sculptor void is situated at 500 million light-years, and the Canes-Venatici void is the most remote at 600 million light-years. They do not just occupy different positions, they form a distinct sequence in their distance from Earth. This sequence holds profound significance. The light we receive from the Canes-Venatici void began its journey 600 million years ago, allowing us to see the structure as it existed in the distant past. Similarly, the light from the Sculptor void shows us its state 500 million years ago, and Eridanus offers a glimpse from 400 million years in the past. Boötes provides the most contemporary view of the 4. What we are witnessing is a form of temporal evolution. These 4 voids appear to represent different stages in a single developmental process. Canes-Venatici displays an early, nascent structure. Sculptor is visibly more developed, and Eridanus even more so, with Boötes appearing nearly mature. It is as if we are watching these incredible objects grow and change over cosmological timescales. If one projects this developmental sequence forward, it raises a compelling question. What would a fully mature structured void look like? Assuming the Boötes void is at 90% of its development, what emerges when it reaches completion? The other voids provide clues, but not a definitive answer. One trend, however, does emerge with clarity. The voids themselves seem to grow larger over time, and the lattices of galaxies within them become more intricate. The frequency of their radio broadcasts decreases as if the structures are expanding and their internal mechanics are slowing down, or perhaps as if they are winding up, gathering energy for a future activation. Prompted by these discoveries, another team began a search for even more of these objects. They meticulously analyzed data from all sky surveys, looking for any void that contained geometrically arranged galaxies. Their search yielded 6 additional candidates. While the evidence for these is less certain than for the confirmed 4, they are highly suggestive of possible structured voids at various other stages of development. If these candidates are eventually confirmed, it would mean we have identified 10 structured voids within the observable universe, with the likelihood of more existing in regions not yet surveyed in detail. This implies that such structures might be a common feature of the cosmos, with potentially hundreds or even thousands existing throughout space. The sheer number suggests some kind of production process is at work, creating structured voids on a regular basis. This points to one of 2 possibilities. Either it is a natural process that we do not yet understand, or it is the result of deliberate construction on a galactic scale. In either scenario, the universe appears to contain an infrastructure we never knew was there. A comparison between these structured voids and ordinary voids highlights their uniqueness. Normal voids exhibit simple expansion. The galaxies at their edges flee the interior, causing the region to empty out over vast periods. No complex activity occurs within them. Structured voids behave in the opposite manner. Galaxies within them become organized. Lattices begin to form. Activity levels increase. They grow more complex as time passes. It seems there are 2 distinct classes of voids, simple and structured. The simple voids are understood as natural consequences of cosmic evolution. The structured ones, however, are something else entirely purpose-built, or at the very least, actively organized. The universe, it turns out, is not uniform. It contains processed regions, areas where something beyond standard cosmic evolution has taken place. The four confirmed structured voids share another intriguing commonality. They are all aligned with massive complexes of galaxy superclusters. The Boötes Void is situated between the Virgo and Hercules superclusters. The Eridanus Void borders the Cetus supercluster. The Sculptor Void is a neighbor to the Fornax cluster, and the Canes Venatici Void lies near the Coma supercluster. This positioning is unlikely to be a coincidence. It suggests that structured voids form near regions of high galactic density, leveraging their proximity to these concentrations of galaxies. Perhaps they draw in and feed on nearby matter, or maybe they require these dense surroundings to clearly define their boundaries. Whatever the reason, the correlation indicates that these structures are not isolated phenomena, but are integrated components of the large-scale cosmic architecture, like nodes in a vast network, or elements within a much larger system. Researchers are now looking for direct connections between these structured voids. Is it possible they communicate with one another? Could their radio broadcasts be synchronized in some way? By calculating the light travel time between the voids, scientists can check if the periodicity of their signals accounts for this propagation delay. Early results have shown some possible correlations. For instance, the 14-day signal from Boötes and the 28-day signal from Eridanus differ by a precise factor of 2. This could be a coincidence, or it could indicate a direct relationship, with one signal being a harmonic of the other, much like octaves in music. If these voids are indeed communicating, they would form a network spanning billions of light years. Messages would require hundreds of millions of years to travel between the nodes. Yet, on cosmic timescales, such a network could still be functional, passing information across the observable universe over entire epochs. The purpose of such a network could only be imagined, perhaps to coordinate cosmic engineering projects, to monitor the evolution of the universe, or to implement some grand design that requires coordination across vast distances. The possibilities are staggering. Humanity has discovered not just a single anomaly, but a pattern of anomalies, a system, an architecture built directly into the fabric of the cosmos. We believed we understood the large-scale organization of the universe, but we were mistaken. The universe contains an infrastructure, and we have only just begun to notice it. This changes our understanding completely. The universe is not what we thought it was. Empty space is not truly empty. Voids are not merely passive. And cosmic evolution is not a purely natural process. Something else is operating at scales we can barely perceive. These structured voids represent the largest coherent structures ever discovered by humankind. They stretch for hundreds of millions of light years. They contain galaxies arranged in precise geometric patterns. They broadcast signals across cosmic distances, and they have maintained themselves for billions of years. Nothing in our understanding of nature behaves this way. Nature, through gravity, creates clumps and filaments, resulting in random distributions that are smoothed out by physical forces over time. The structured voids are different. They appear organized and purposeful. Whether they are artificial creations or a sign of new physics, these phenomena are fundamentally different from normal cosmic structures. If they are engineered, the meaning is stark. An advanced intelligence operates on a scale that makes human civilization appear bacterial. These beings seem to manipulate entire galaxies with the ease that we might handle individual atoms. They construct objects that are built to outlast most stars, and may even engineer the fabric of space-time to serve their purposes. The conclusion is that we are not alone, not by any meaningful measure. The universe is home to entities so far beyond us that we cannot comprehend their most basic technologies. We are like ants who have found a power grid. We can observe it and measure it, but understanding its function, or its reason for being, exceeds our capacity. If the voids represent a natural process instead, the implications are equally profound. This would mean physics operates in ways we never imagined. Perhaps higher dimensions exist and interact with our own, or parallel universes make contact at these specific points. Space-time itself might possess an architecture we never suspected. Either interpretation forces a rewriting of our textbooks and demands a complete reconsideration of cosmic evolution. The universe is not a simple story of expansion from a hot, dense origin, gradually cooling and organizing under gravity. Something else is taking place, something we are only now beginning to see. The structured voids are growing, and their activity increases year by year. Whatever process creates and maintains them is accelerating. The void in Boötes is approaching completion, while the others follow their own developmental paths. On cosmically short timescales, these structures will reach maturity. The question that follows is what happens then? What do fully developed structured voids actually do? The answer will likely determine the fate of our universe. One possibility is that they are seeds, templates for a new kind of physics. When they activate, they could convert the surrounding space to their own type, with normal physics changing to the physics that operates inside the voids. This conversion would spread outward at the speed of light, eventually transforming the entire cosmos. Such an event would be catastrophic for life as we know it, since biology depends on very specific physical laws. If those laws change, existing organisms could not function. Stars might burn differently, and atoms might bond in unfamiliar ways. Everything familiar would cease to work. An alternative idea is that activation creates connections. The voids might link up in some way, forming a network that spans the observable universe. The purpose of such a vast network could be communication, transportation, or power distribution. The scale is beyond anything we can imagine, but the structure itself suggests a certain utility, which points to a more optimistic possibility. The voids could be a preparation for something on a cosmic scale. Perhaps the universe is approaching a transition point, be it vacuum decay, heat death, or a big rip. In this scenario, the voids would be an infrastructure for survival lifeboats or safe zones, regions where reality can persist through a cosmic catastrophe. If advanced civilizations did build the voids as survival structures, perhaps they intend to share that protection. Discovering them might even be the test. A civilization that develops enough technology to see the voids might earn consideration for refuge. Failing to notice means facing whatever comes unprepared. This is, of course, speculation and hopeful thinking. We have no evidence that the voids serve a protective function. They could be neutral infrastructure, or they could be threats, weapons, traps, or experiments that could go wrong and destroy immense regions of space. Our observations continue. Every major telescope now monitors the structured voids, watching for changes, tracking their development, and searching for clues about what comes next. The scientific community has mobilized. This is being treated as the most important discovery in human history, and understanding it has taken priority over everything else. Governments are debating policy. Should we attempt to make contact by deliberately sending signals toward the voids, or should we maintain silence and just observe? The question divides opinion sharply. Contact might bring benefits like knowledge, technology, or even salvation. Or it could bring a kind of attention we cannot handle. An argument exists that the voids already know we are here. Our electromagnetic emissions have been leaking into space for decades. Radio and television broadcasts, radar pulses, military transmissions. If anything is monitoring the voids, it likely detected our signals long ago, so silence now would change little. Some scientists argue for active messaging, for deliberate attempts to communicate with whatever controls the voids. They suggest we show them we are intelligent, curious, and peaceful, and request a dialogue to learn what they know about physics and the universe. Others counsel extreme caution. We are infants compared to the potential builders of these voids. Initiating contact from a position of such weakness is dangerous. It seems better to learn more first, develop our technology, and understand what we are dealing with before announcing ourselves. The debate continues, but it might be moot. The voids are activating on their own schedule. Whatever is being built is approaching completion. In years or decades, the work will be finished, and the universe will change. We are now passengers, observers of processes far beyond our control. One certainty has emerged from this. Our descendants will live in a different universe than we do. When the structured voids complete their development, reality itself will change, bringing new physics, new structures, and new possibilities. Whether this is for the better or worse depends on what the voids are for. Humanity stands at a threshold. Behind us is the familiar universe of galaxies and stars. With physics, we mostly understand a cosmos that makes sense. Ahead lies unknown territory, a universe of structured voids, geometric lattices, and signals from unknown entities. It contains an infrastructure built on a scale that dwarfs comprehension. We cannot go back. We cannot unlearn what we have discovered. The voids exist whether we acknowledge them or not. The only choice is to move forward into whatever new reality awaits. The void in Boötes is no longer an astronomical curiosity. It has become a herald, an announcement that our universe contains depths we never imagined, that cosmic evolution follows scripts we did not write, and that intelligence or physics beyond our understanding is shaping reality. We found something hiding in the void, something vast, ancient, and transformative to all we thought we knew, and now it is waking up. The countdown continues as the structures approach completion and the signals intensify. Year by year, the voids become more active, more obvious, and more impossible to ignore. Something is coming, something the voids have been preparing for over billions of years. The universe is about to change in ways we cannot predict. We discovered it just in time to watch it happen, to witness the transformation, and to learn what structured voids are for. The void is not empty. It never was. It contains the future. The future is drawing near.